Today's first speaker, Professor Dr. Jeremy Lecour, Professor, University of Geneva, Switzerland. Professor Jeremy Lecour is a distinguished scholar in chemistry whose academic voyage began at the École Normale Supérieure, ULM Paris, leading to a PhD from the University of Texas at Austin under Professor Philip T. Magnus. You know, Professor Magnus was a legendary name I used to hear way back in 1980s during my stay at IIT Kharagpur, courtesy to my teacher, Professor Tarun Kumar Sarkar, probably know him, who was also pursuing research on silicon chemistry at that time. Nevertheless, following a prestigious postdoctoral stint at Harvard University with Professor David A. Evans, another legendary name all of you know, he joined the University of Geneva's Organic Chemistry Department in 1995, where he currently holds a revered full professorship specializing in asymmetric synthesis and catalysis. Professor Lecour's influence transcends academia. He has chaired international symposiums and served as president of the Société Chimique de Geneva. With over 240 publications and 340 lectures, his impact is profound and far-reaching. His exceptional contributions have earned him numerous accolades, including the prestigious Warner Prize and medal from the Swiss Chemical Society, the Grammaticakis Newman Prize from the French Academy of Sciences, and the 2006 Holger Elkman Lecture Honor at KTH, Sweden. Furthermore, he has held notable positions such as President of the Geneva Chemical Society and Chair of Chirality 2008, the 20th International Symposium on Chirality. I will not prolong it further because, like you, I am also very keen to listen his valuable talk. So today, Professor Jeremy will deliver a talk on a popular topic entitled Stereoselective Synthesis and Catalysis with Reactive Metal Carbenes. I now request Professor Jeremy to occupy the dais and deliver your talk. Thank you.
Thank you. Wow, it's packed actually. I was sitting in the front row. Thank you so much, Mr. Chairman, for the way too kind introduction. Thank you for the most pleasant evening and this invitation to come. It wasn't that, that last minute, but having the opportunity to come here to discover this PPP actually program is very important. I was the Dean of the Faculty of Science for 15 years, and I just dreamed to do something. You've done it, okay? So congratulations for this very strong relationship with the colleagues of actually Hyderabad. This is this kind of initiative which are strongly needed. We're not as good as you are actually in Switzerland, unless even if the repetition is maybe there. Okay, so but let's go about science maybe. So my group does what many people do: structure, function, reactivity, and hopefully methodology, okay? But when we do structure, we are very inorganic in the sense. We look for three things, okay? We look for simplicity. We want compounds that we make basically in one step or two steps. And trust me, these compounds are really made in one or two steps actually, and batch way actually for the moment. We look for chirality. These derivatives are chiral due to their three-bladed geometry, or let's say helical backbones. And then we look for charges. And why do we like charges? Because it's one of the easiest ways to go in a supramolecular fashion. Because we should always remember that the cation has always an ion and vice versa as a partner. So everybody, I've seen a beautiful setup for photocatalysis. Many people use ruthenium complexes. And they tend to forget that the little brother, the ion complexes, so important for material science, has very different properties. Because upon photoexcitation, you have extremely fast spin crossover. And one of the consequences in terms of chirality is that you have a very fast, actually, racemization. So the two enantiomers are in a 1-to-1 ratio. And there's nothing really that you can do to control this. People put chiral ligands, but the induction is never really good. You're too far to control the geometry of the center. However, if you have counter ions, and if your counter ions are well designed, they're chiral, And if you can bring these ions together, and it's so easy, just lower the polarity of the solvent, okay, what will happen? You create diastomic interaction, and in coral form, there is a single diisoisomer, single enantiomer. Okay, so these are actually all studies from the group. Why I'm mentioning them is because a young, he's really young actually, friend of mine, Matteo Coman, created a setup to do ultra-fast circulodichroism. We're talking picosecond circulodichroism. You can now test the curability of excited states. And I'm excited actually by it, and not on the picosecond level. And this is just one of the things that we just reported in the paper. It's an experimental proof because you can follow basically the state of the famous radiate twist mechanism of atomization. You can go to physics with this kind of process. Most of the new 5 or 6 generation beamlines have actually linear or circular polarized actually light components. We can go to really new physics and essentially helical dichroism. Don't let me go into these topics. It's really, I mean, incredible actually progress in physics. But now, today, I'd like to speak about reactivity. As medicinal chemists, SAR is natural. Structure-activity relationship, you modify actually your structures. We in material science need to do the same thing. So if you are interested by controlling properties, electronic properties, nowadays late-stage functionalization becomes natural. But on polyaromatic derivative, can you really target very, very cleanly site-selective positive? Can you do it multiple times? At every given time, can you introduce modifications that are helpful? So if you like to imagine actually being able to control 4 times in a row like a CH insertion, check this paper. We had a lot of fun trying to do this kind of chemistry in an iterative process. We like simplicity, I told you. How can you make it as simple where a single compound will be an electrophile and an oxidant? Imagine this. And if you do, you just need to put an enamine, and in one pot, the molecule will sacrifice itself to make carbon-carbon coupling. No catalyst, no nothing. And this is a chiral signing, so you will have actually fully extended system, absorption in the near-infrared, emission in near-infrared, very strong for instance optical property, one-step synthesis. Okay. Finally, how many of you have done Hartwig iridium catalyzed borylation? You can raise your hand. In CH activation, for me, in this domain, this is the must reaction because you access all, actually, of course, the boron system with which you can do Miura-Suzuki coupling. This reaction is amazing. Here, we just introduce it to functionalize a position which was never accessible in this type of chemistry. And then with that, in 1 or 2 steps, following hard, group chemistry, you can put donor groups, you can put electron groups. In material science, I don't know if you followed the field, there is an extremely importance given to open shell molecule. Radical compounds are becoming the thing of the day, essentially in material science. These SOMO transition are becoming really essentials. We're creating compounds which can really absorb it, really very, very strong in infrared, and engineering compounds which, as far as I know, have a level of dissymmetry factors which are quite unusual for this kind of very, very low energy light. Hopefully, we get a good decision sometimes. Okay, so already 2 minutes, but I wanted to give you the background because for me, doing good synthesis for methodology, you have to apply it also to material science nowadays, at least in the industry, in an academic setting. Okay, so I like charges. And how can you use charges in terms of reactivity? And we decided some years ago to go to ELIS. And ELIS, as you know, is a carbon ion, for instance, with formerly positive heteroatom next to it. Usually it's an oxygen, a nitrogen, a sulfur. And it's usually represented like this. And we don't like to represent ELIDs as a complex with a metal ion. And this is a big mistake because I will hope to demonstrate most of these ELIDs are actually metal bound. And the reason for this is we generate them by a simple addition of a Lewis base, like THF or dioxane, you will see, to a Fischer carbene. Okay? So it's just complexation. It gives you the metal bond species. And these kind of complex are coming just by diazo decomposition. So very simple, again, one-step chemistry. What can you do with it? So if you want to make ELIDs, you better work with so-called acceptor diazo derivative, because you want very, very electrophilic carbons. So I just want to make sure that OPRD, okay, has a very, very good journal. And this is this review which actually makes the survey of all diazo compound. Trust me, after reading this, and we knew it before, you don't want to work with any other class of diazo compound in batch mode. Go to flow. This is the way to go even for diazo chemistry, but these compounds are actually really safe. But apart from that, very strongly electrophilic carbons, and then when we add the base, indeed we form the metal bond. So what I will try to entertain you and to show that under the same class, exactly the same conditions, you can make macrocycles in one pot, you can make actually really interesting product of rearrangement depending on the metal. And let me start with a very serendipitous discovery, and it's really green process if you don't account for the preparation of actually the diazo product itself. You just mix in the solvent like 1,4-dioxane, which is both the solvent and the reagent, this compound. You will see the only byproduct is dinitrogen. You cannot make it, at least in principle, more sustainable than this reaction. What happens, this is actually, you remember the Fischer carbon, this will be the rhodium complex. This is electrophilic, the nucleophile will add, and I write the metal-free species because we even have an X-ray structure. It's a minus 50 degrees X-ray structure of an ellipse. We haven't reported it yet. The NMR at minus 50 degrees is so interesting, but we still have to completely rationalize everything. But what can happen here? For the old guys who remember Peter Big's work or Asian Moser, actually trajectory for SF2, this compound cannot self-immolate. The only pathway for it is a dimerization. This is the redetermining step, okay? And it's a second order redetermining step. So for macrocyclization, if your redetermining step is second order, what do? You concentrate. Every time you concentrate by a factor of 2, your macrocyclization actually, is faster by a rate of 4. So we can even basically run at higher concentration. By a 1 molar concentration, we get these compounds. In 20% yields, we need only 200 milliliters of dioxane. Probably could do better. Talking to with Adnil. This is the catalyst loading. So actually, my students, they don't like to wait 4 days. They sacrifice actually 10%, and in 6 hours, this is exactly what we produce. So just to show you the kind of diversity we do, if we start from dioxane, we make this derivative, we HB this one, with THF, of course, it's the 16-member ring, and then, of course, you need nitrogen. And then we stumble for many years on the roadblock with nitrogen. So we managed to publish a study a few years ago. It looks somewhat good. The catalyst loading looks a bit not as favorable. We need to put, of course, electron withdrawing groups of the nitrogen because nitrogen is usually better Lewis base or better nucleophile than oxygen. Okay, everything seems to be fine. We have to select this rhodium catalyst, okay? The yields are moderate, but it looks good. But we didn't find this before we did the mechanistic studies. So please always go to kinetics, always go to isolate the byproducts, because then you will discover things every given time. So when we do reactions, when we're in discovery mode, we don't use this catalyst loading, we use that catalyst loading. And then the yield is lower. And the yield is lower because you form a major, it's not a byproduct, it's 50% yield, you form this very weird looking derivative. How can you generate these compounds? Well, if your nucleophile is not a good enough nucleophile, a carbene will undergo Wolff rearrangement to the ketene. And then here, this is a carbonyl group. You can, and I will talk about this reaction a bit later. It can form this dioxoline derivative, but clearly here, this process is favored by a high concentration of rhodium. It means that this must be the redetermining step, which would be then second order in metal. How come this can be second order in metal? I don't know, but experimentally, this is what we find. So now we know we need to reduce a bit the amount. And then again, you talk to your inorganic colleagues, and they said, you know what would be good is not to have mesylate, whatever, but groups. We want to have a malonate group here. And me, I didn't say, well, that's not a problem. Let's make the malonate of these compounds. And then we stumbled on a reactivity, which might actually be useful for medicinal chemistry, is how on an unhindered, very, very basic actually derivative, how to make the NH insertion of a carbene. Trust me, and you can look at this literature, including by beautiful work in India by Muthuswamy. it's especially impossible. Either you have to use aniline, which are not nucleophilic, or extremely hindered imine, which will not poison the catalyst. Okay? And the ruthenium catalysis we do allow us to do it. And then I really have to give credit to Pondichéry and Professor Siva Sankar, who in water used actually in this paper iridium catalyst. Mechanistically, I'm still not completely attuned, but we tried actually his catalyst. It's wonderful. And the best is one-to-one stoichiometry. No even any need for any excess, essentially, of the dyes, or even like acetylene and other compounds can react. And just as one proof, just to show you that it can go on nitrogen, even extremely good nitrogen, due to actually geometries we can make, for instance, the macrocycles and the inorganic compound, the inorganic derivative they wanted to have. Okay, so, and then again, serendipity. So I told you that this reaction is general. What I didn't tell you is that we always get a lower yield when we do the reaction with THF. And we get a lower yield because we isolate the byproduct. I always go in my group, you better characterize your byproducts, okay? And this byproduct was a total unknown, actually, in the field of carbene. It's not a carbon-carbon CH insertion. It's an oxygen-carbon 1,3-CH insertion. It's unknown. So if it's unknown, let's go about making this kind of derivative. Even if you don't see immediately a synthetic value for it, just try to make it, actually. We must have stated 30 rhodium catalyst. At best, maybe we had a 20% yield of it. So at this kind of stage, how is your reasoning, okay? The reasoning is we can never go at this kind of compound with rhodium because we are metal-free. So we need to go to metal bond catalysis. And there was some evidence in the literature that the CP ruthenium complexes could be good. Okay, so if you want to put like bipyridine or phenylalanine ligand on CP star, especially chemistry, this is really chemistry developed by Christian Bruno in Rennes. I want to really mention him. He was also doing a bit of CP. CP ruthenium catalysis is very well known in Geneva from the postdoc supervisor of Krishna Kalyapan, which is Professor Peter Kundig. And these compounds, by the way, we mentioned yesterday palladium leaching, and catalysis sometime. You have to be very careful with these compounds. They make beautiful ruthenium nanoparticles when you start to itch, so 80 degrees and all these things, so be careful. The BARF derivatives are much more stable both in the bench and also at high temperature. But anyway, now under exactly the same concentration in the same stoichiometry that the reaction that gives you the macrocycle, the ruthenium gives you exclusively 98% of the crude, the 1,3-CH insertion. This is also another reaction I'm not going to detail. Usually when you put carbene, electron-poor carbene on the epoxide, the only thing that you do, you extrude the oxygen, you get the olefin. These compounds give you exquisite scene opening. You go from a cis epoxide to a cis product with essentially retention of configuration. It's SN1, stereoselective SN1 chemistry. You cannot discover this kind of process elsewhere. Okay, so now I'm going to show you essentially unpublished results for the next 20 minutes. And this will start actually not with ruthenium, but it will start with copper catalysis. So many of us nowadays want to target carbonyl groups, and carbonyl groups of amide in particular. I guess you all know this, a lot of nickel catalyzed, for instance, process, and it's really important to do it. We decided to go at it with carbenes, and I'm going to show you a rearrangement that, again, could not be expected. It's specific to copper. We usually don't use copper, but it's specific to copper. And let's see what happens. So you tack with this kind of oxazolidinone. On the aromatic ring, you can put all kinds of para-substituted, and this is a selection of it from electron-rich to electron-poor. At the meta position, you have to put electron withdrawing groups. The reason is actually if you put electron donating group, we have direct cyclization to the pyrrolizidine directly, which can be interesting anyway, okay? But if you want to stop, we put electron withdrawing groups. Our ortho positions, it doesn't work very well. On the migrating group, so here the blue X is either ester group, it can be a phosphonate, it can be even an ester group that migrates actually from the carbene to this position. Seriously, mechanistically, it's interesting. You can make lots of different actually variations actually at various positions on the pyrrolidinone. It's not a problem. And its diaster selectivity can even be excellent, and then your specificity as well. I personally don't know what is a copper carbene. Sorry, let me rephrase. I don't know what is acceptor copper carbene. Beautiful work by Alois Fürstner recently on donor stabilized carbines. Amazing crystallographic work and spectroscopic work. So this is wrong. But these compounds for me are a black box. Then let's say it's electrophilic carbene. You have the lone pairs of the carbonyl groups. It can attack the center. We form what we're looking at, metal bond elide. And when you have carbonyl groups, usually the reaction that happens immediately is a kind of epoxide formation. But this usually leads to actually deoxygenation process. In our case, in the geometry and the reactivity, we see a very unusual 1-2 shift giving us the products. Actually, 1-2 SI shift in intramolecular fashion can be faster than alkyl or alkyl substituted. There's some literature on this. Personally, I didn't know about it, but we wanted to do. So then you have a new class of compounds. Can you make something useful with it? And medium-sized ring and constrained medium-sized rings can be important. So here is a new reaction that we discovered. This is a product that you just saw. We just need to treat this compound with hydrazine. You form an intermediate. We add acetic acid to provoke the reaction, and we get in one pot this 9-membered ring with a phenyl ring, and also this important heterocycle for actually medicinal chemistry. All kind of ester groups, not surprisingly. These different groups comes from actually substitution on the initial pyrrolide lactam, and this, of course, comes from the substitution of the aromatic ring. Here, you have a mixture of regioisomers, and this you will see can be explained by the mechanism. So upon hydrazine formation, we can isolate. We even have X-ray structure. We form the cyclic derivative, but it remains at the actually aminocarbinol stage. When we add the acid, we provoke the elimination of water. We form the imine, and then now a tautomerization can give you the enamine. And everything is then absolutely beautifully set up for a 3,3 sigmatropic rearrangement with de-aromatization of the aromatic ring, okay, to give you this imine, the 9-membered ring, and after prototropy, you do this. We like mechanism. How could we prove that it is a redetermining step, even if we had calculations for this? If you imagine that this carbon goes from sp2 to sp3 in the transition state, then you just put a deuterium. You look for kinetic isotopic effects, secondary, and we have a reverse kinetic isotope effect. We're happy with this, small, but enough. Okay, so this is the kind of really process that we plan to report sometime soon. Again, a carbonyl group is really essential, and not too many of us are targeting this kind of compound. But just a quick say, for many, many years, since Noyori and many others, Greg Fu and many others, we all wanted to use this oxetine with this vinyl bond to do 2,3 Stevens rearrangement. We can, none of us, we were always going the THF, the 1,2 rearrangement, never the 2,3. We just submitted the paper, and the trick is nothing to do with the catalyst or the diazo, is to add this geminal dimethyl group that changes the conformation of the intermediate, and you can access now a 7-membered ring, you can access the oxepine, and I think this would be quite useful actually for our medicinal chemistry, this kind of rearrangement. Okay, so back to ruthenium. This is the love of the group for the basically last 15 minutes. And here is a transformation who looks basically simple, and for a search in the literature was this transformation from a ketone to enol malonate. There was only 3 examples in the literature as byproducts of reaction. Okay, let me try to show you this. So we can even start from cyclobutanone. We can make the enol malonate, and then all the classical series. This just look like Switzerland, so I just put it in red, but don't matter, okay? We can put various substituents here. It all works. This is basically expected. Now this has become more interesting. The regioselectivity is very good. Here is the conjugated one. It's not surprising. Here, it shows that we form the so-called kinetic enolate. Okay, this is much more important. You never want to make the thermodynamic compound if you can make the kinetic. Okay, so we make the kinetic derivatives, sometimes absolutely fantastic regioselectivity. Here it's a bit more complicated, but still, Okay, we can discriminate a bit around the size. All kinds of malonate derivative can work. Okay, but quickly, why are we excited by this new chemistry for us? Because out of one ketone, you will form maybe one enolate, but it's as if you're forming a dianion. Okay? I won't show you how we can directly actually do allylic oxidation and other things and azide introduction, bromination. That I won't show. But I will just show how we can use in one pot essentially the double combination of the malonate reactivity and the enol reactivity. So on the strong bases, in particular KHMDS, we do the irreversible deprotonation. We can add more than 30 electrophiles with this compound. Let's suppose we add a propyl chain, then we can do first type, actually metallation, to give you the, in a way, a skip diene here, the exocyclic diene very nicely. If you just put, a little bromide, then you can do a classical, like let's say a silver or copper catalyzed system to give you now the skip diene, okay? If you were to put from dibromoethane this side chain, you do the radical, you will get the 5-endo trig process to make the styrol compound. Okay, fair enough, it can be interesting. But again, serendipity will give you maybe an example where you can make a 6,5 highly functionalized transfused derivative, and then you have to study this in more detail. Okay. So the acyl bromide is actually commercially available. It's actually pretty cheap. And we deprotonate, we make these compounds. Then we use very, very mild, actually, photocatalysis conditions. The reducing agent at the end will be a hydrogen donor is a Manchester, which is here. I show for the moment a clean orange, it's a bit more subtle like this. We use blue lead, and we get these kind of products. 6,5, 7,5. Here, the diazo selectivity is moderate. By the way, the major actually byproducts, major diazo isomer have the always the group actual. I could discuss this if you're interested. Yields can be moderate, and we know why. Okay, because you will see mechanistically there is something at the end that I'm not completely understanding for the moment. Again, my Swiss cross gives us only 15%. This is where we really discovered maybe the only issue that there is in the mechanism. So first of all, the first thing that starts is in situ, we protonate the acridine to the acridinium, which is a much better photocatalyst. Now, upon irradiation, we form the excited states. This can actually be reduced by actually the Hunch base getting itself oxidized. And now we have a very strong, strong reducer able to make the radical anion, which will expose the bromide and give you this radical. Now the reaction has clearly to be a relatively rare 6-endo trig. We form this radical. This radical, and I think this is undocumented, can fragment to give you now this very stabilized electrophilic radical. And at that stage, normally you stop, because there is no way that this radical can attack a carbonyl groups. So two pathways. One that I tend to favor, but I'm not sure anymore. This is the further reduction to the carbon ion. Then it's essentially, an aldol-like process, a Knoevel-Allegan-like process. Okay, and then you have to find a proton source to give you the product. But with a 12-membered ring, we isolate with 50 or 60% the open form. And you could consider that this is only just, a hydrogen transfer give you this. Well, what we discovered is these compounds actually give us reversibly this derivative. Calculation could even, tell us that this could be possible. I don't know. It's a kind of, we don't need light because it's a kind of Norrish-Yang process without light. Very mysterious, unpublished because of this. But still, this is the kind of chemistry which excites us, and we're generalizing this also in reduction process chemically, and including electrochemical synthesis, new kind of PD process that can be done, I think, and kind of annulation process that could not be done unless you get in one pot from a simple ketone, two functional groups. This is very important. Okay, so I think I'm doing okay with time. Let me try to convince you of that you still need to do totally useless fundamental chemistry as an academic. Okay, and I'm going to try to bring you to this. So we love carbonyl groups, we love carbenes. And we discovered, and this is really specific to ruthenium catalysis, that you can form very, very nicely dioxolene derivative. It works on aldehyde, so acyclic derivative, on acyclic ketone, on cyclic ketones. So you imagine that the lone pairs here react with the carbene, give you this type of beta-ene that closes to give you the product. Okay, fair enough, it's quantitative, it's nice, but what's the use? Well, it might start to be useful because you can do it on lactones. Well, you can do it now on lactams. Okay, so you remember the copper gives you the rearrangement, ruthenium gives you this chemistry very, very cleanly. And then it was a bit of a joke. We started, well, can we do it on cyclic carbonate? And we got this product. It was a footnote of an organic letter paper. And then more recently, I started to do it. But why did we use such a simple substrate? Let's just make a simple modification. Let's just put 2 R groups here. If you look, this is the product. But if you check, this is the chiral version of the product. Because these are 2 enantiomers. These carbon have formally 4 different oxygen groups. And then you check the literature. Is there any mention that the carbon with 4 heteroatoms can be even stereogenic and resolved? And I will go back to you on this a bit later. So we did a very quick series of derivatives. Some of these yields are really excellent. This is preparative yield, and even on a 1 gram scale. And then, you know, it's easier just to do the HPLC, semi-preparative HPLC. And then you separate the enantiomers. And then, okay, these compounds, doesn't have many chromophores. It has only an absorption at 250 nanometers. But we can get a CD for both enantiomers. The compound is conformally stable. But with 4 oxygens, there's not so many variations that you can do. So we started to imagine, let's go back to my good old oxazolidinone. I come from Evans. Even with a Bock compound, can I distinguish a carbamate outside from inside? It works very well. And some of these compounds, these are isolated yields of carbamate trapped with these compounds. Okay? We can even trap the compounds with twice a Bock derivative. Okay, so here the yields are low because the reaction is extremely slow and most probably for steric reason. So then we could even do, tosylate or actually the methoxy versions. This is the X-ray of it, so we're really not imagining anything here. And then this is a series which I couldn't believe that we can even make it, okay? These are aromatic, directly product from anilines, basically carbamate. The yields can actually be fantastic. And so to contrary to what I was expecting, these compounds are actually more stable than these derivatives. So mechanistically, it's also quite intriguing. So again, coming from Evans, I had to do a chiroxazolidinone. We got a very low diaster selectivity. And again, what did we do with these compounds? Can we even separate on silicon GR chromatography the diastereoisomer? We can do. We can even get the X-ray structure. We knew the configuration of this center, okay, so it just confirmed it, but we can then get the configuration of this Spiro center. And we also are establishing this in collaboration with also the HPLC, separate again analytically or semi-preparatively the enantiomers. We have got pretty clean, actually, compounds again with this. And by the way, when you have a Bock, you need to usually go to 60 degrees to do the NMR without the rotamers. Here, it's a bit more complicated. We need to go to 80 degrees, okay, to get a clean NMR spectra. It stays as a single, actually, enantiomer diastereoisomer. These compounds are extremely rock stable. So, if you're interested by chirality, we all know these compounds that we know as the first, actually, compound with a stereogenic center. None of you, or very few of you, maybe know that he has never been made as a single enantiomer, by the way. The 2 enantiomers, one was made in 90% in EE, the other one is 70% EE, by the way. It's one of these compounds which we all teach as single enantiomers. This is the fantastic chemistry from Peter Schreiner and the topological equivalent. These are the famous type of cryptochiral compounds. It's a stereogenic center with 4 identical carbon atoms, or here isotopically different. But there is only one mention in the literature of a stereogenic center with 4 heteroatoms. The compound is not labile. It will racemize actually rapidly in solution. So this class of compounds, well, hopefully they will have a future. Okay. And even in pharma, maybe it has hemilabile group to liberate actually compounds. And if you could, I'm happy to discuss this kind of, maybe protect crazy, hemilabile groups, for protecting a compound to go through a barrier and then releasing a derivative. I think there's a lot of future behind, behind this kind of chemistry. Yesterday, I was provoked by Anil, who says it's going to be philosophical. Okay, so, okay, let me try to exercise in this. But before that, just a summary. If we can really go to compounds which would be very difficult to imagine, okay, without the chemistry of carbines. And one chemistry which I didn't detail, which of course in India is wonderfully represented in Chennai by Professor Ambarasan. This is the chemistry of alpha aminocarbines. We did a lot of those natural, medium-sized ring or large-sized ring. This is this kind of, we start from trigger base, 5 steps in a row, but I won't discuss this. What I want to discuss today, and I will use a very Swiss, okay, presentation, is this, okay, scheme. For those who know a bit Switzerland or who like Toblerone, okay, you like Toblerone, okay? This is this is what you see. This is called the Matterhorn, or in French, the Cervin. Amazing. You have to go to Zermatt to see it. Okay. Thank you so much. And I'm going to use this to show that how you can go away from target-oriented synthesis. Doesn't mean it's not important. I mean, natural product synthesis is fantastic. Diversity-oriented synthesis, it was so important in industry. Still, okay. Function-oriented synthesis, that's material science. Me, this is what I like. Okay, or chemical biology. Structure-based organic synthesis, that's something a bit different. Okay, but we like, and we should never forget this, simplicity-oriented synthesis. All the things we discovered is because we take solvent. No, it's fine, please. Okay. We just take THF as a solvent and a very simple, diazo, and this gives us the room to explore many things. Chirality is so important because you discover things just because you're looking for a property, and this is a kind of disparable compound. Okay. Catalysis-oriented. You see how by changing a catalyst, you change a manifold. Always, even if you already have the product that you want, try another catalyst because you will get to the product that you don't want, and it might be more interesting, okay? And then serendipity-oriented synthesis. And I think our group is engineering serendipity. Can you engineer serendipity? And here is the concept for Anil, okay? So when we do chemistry, the major problem that we have is usually kinetics, and actually the barrier of activation that we try to bring down by catalysis. So we try to bring it down. You can try to erode the Matterhorn. It will take some million years, okay? So bringing down is very difficult. But what about lifting a compound? This is what you do nowadays with photocatalysis. I challenge the idea. This is exactly what I do when I make a carbene. I just basically boost the reaction by 20, 30, 40 kilocalories per mole of energy. And once you're there, you don't need really to talk about catalysis because the barrier is just so low. So you will drop to the bottom of the valley. You know this, but you don't know where you drop. Because with rhodium, you might go this way. With copper, you might go this way. Or with ruthenium, you might go to Italy. And this is what I like. This is the serendipity that comes from the metal catalysis, which allows me always to essentially discover the unexpected, and this is what we were looking for. So this is my concept slide, Anil. With that, I have to thank my group. Actually, so very, very briefly, I just mentioned the carbocation, and this was the work of Joanne, Geraldine, Yana in particular. This is actually more, it was more on the carbene, actually a story, and this was, I mentioned the work of Elodie, of Léo, Alexandre, Guillaume, Claire, actually Yana, Daniele, Julia, and Zhuang. Many great collaboration with also teams in Geneva and spectroscopists. These are actually fantastic people. Funding comes in Switzerland mainly from the Swiss Foundation. I'm strongly indebted by my university. It's really, I like it. I will not move from there. Geneva is another spectacular city. I hope to welcome many of you there. Thank you for the invitation. Thank you for the attention.
methyl malonate enols, and you've got double bond. And if you activate that active center and put it like allyl group or homo allyl group and do the metathesis,
Well,
you can.
very good question. There's only one trouble with this, is that most of the, okay, doesn't matter. So we have enol derivative, and most the Schrock we haven't tried, but most actually, let's say, Caltech type carbene will be poisoned once you have formed the enol, because the enol derivative makes extremely stable carbines. So although you will come from the outside, okay, so you will form the carbene exactly as you mentioned from the malonate, as soon as you've done the metathesis, at some stage you will form, okay, you will give the opportunity to the ruthenium carbene to make the enol one. This one is dead in the water. So far, we haven't found a catalyst. But your questions push me that we should try again.
Yeah, because ruthenium is being tolerated in the system.
Yeah.
So you can make ruthenium carbene out of one of the double bonds.
The first one we will. It's just after the, when we're going to make the metathesis, there is a possibility after the metathesis that we go to the enol carbene, and this one is basically...
You don't know, it's unknown territory.
Yeah, so it's unknown. But yeah, so me, it's, yeah. Okay, I should try it. Thank you. But by the way, actually, the triple bond and the alkyne-alkene metathesis could work much better. So I would be very excited by the molybdenum catalysis, for instance, of this one is different and it could work better. But thank you for... Yeah.
Sure. So I have a couple of questions. I mean, it always amazes to see how you are able to make structures which we assume are not supposed to exist. I'm referring to the single carbon coordinating to the 4 oxygens. But there was this very interesting thing on the copper carbene process that you have expressed on the pyrrolidines to form the thing. I just wanted to ask, I've also seen one example on the pyroglutamyl kind of a system, the product, where there was a carbonyl on the other side of the nitrogen. It's a pyrrolidone. So when you get this spirocarbon, not spiro, but potentially a spirocarbon, tetrafunctionalized, if you have a chiral group as a hydroxyl on the ester, as an auxiliary, instead of a methyl ester, would that lead to some diastereoselectivity or some kind of a preference?
We briefly looked into it.
In general, is that an approach, or in a carbene it might be compromised and we don't?
It's a good approach. Why not?
You can go for an chiral alcohol-based auxiliary.
We always want the catalyst to be doing the work, so we didn't push I didn't show this. We have some ligands who give us maybe 30 or 40% EE, but we'll never get better than this for the moment.
That's more from the...
looking for intramolecular control is a good idea, probably.
Okay, for more as a substrate directed, that was it.
We haven't done
The other is out of a bit of curiosity. In the initial part on the 1,4, the dioxane and all the tetrahydrofuran, if you were to have a deuterio version of the 1,4-dioxane or the deuterio version of tetrahydrofuran, would that lead to some impact?
It works.
It works
Perfectly.
So it has no... The CH insertion still happens efficiently.
Very well.
Okay.
So no, there's no problem. Absolutely zero problem. So we used actually Bob Crabtree's chemistry to put the deuterium instead of the H. We tried it, and actually, what is interesting, I have time for another lecture? No. Okay. So the carbene addition is reversible, and we proved it. And this is the selectivity. It comes from there. It's very interesting. So the rhodium is reversible. The ruthenium. So the initial attack is actually totally reversible. So proton or carbene, ruthenium carbene is the same.
Okay.
So, and because it's not the kinetic, the determining step, we have zero actually kinetic isotope effect. So with the deuterium, so we didn't see it and said, how come we do a CH insertion? It was, 1-to-1 mixture and then of KH over KD. And then that told us, And so we did the calculation and we have a curtain Hammett. So the initial carbene addition is totally under equilibrium. Okay, and actually it's the wrong side, which is even slightly more stable. But as usual in the curtain Hammett, this is the next step, which is the redetermining step, and this is okay, and that explains. So we got lucky.
Yeah. one last, where does the carbon come in the tetra-substituted?
Oh, this is just okay. Sorry, it's just come from phosgene or carbon.
In 13C NMR, I was just curious.
Ah, this one.
Because it must be quite down.
Not so much. It's basically like an acetal, so but a bit. So shifted 96 ppm, 100 ppm or so. No, nothing crazy. No, not so much. Actually, it's quite difficult to see, as you might imagine. There is no relaxation whatsoever.
Yes.
So at some stage, we will even have to label it with a C13 just to make sure that, okay.
Get the intense.
Yeah, we get a very intense peak, yeah.
Okay, after the outstanding talk of Professor Jeremy, now I am going to announce that our second speaker of today's session is that Professor Anil Kumar, Professor, Department of Chemistry, IIT Bombay, India. Professor Anil Kumar is currently a professor at IIT Bombay in the Department of Chemistry. He also serves as a president of the Society for Polymer Science India. His research groups research interests are in the areas of process intensification, optoelectronic devices and materials, nanomaterials, flavors and fragrance, polymers and continuous crystallization. His group has also developed many technologies, including transfer of technology in the domain of hand-filled explosives, sensors and continuous flow processes. For his contributions in this field, he has been awarded with the 2017 NASI RIL Platinum Jubilee National Award for Application-Oriented Innovations.
Full page.
Apart from research, his other hobbies are teaching, sports, technical final analysis, magic and music. He has developed an outreach program based on the science and magic to promote teaching and practice of science amongst scientists, students and research scholars. He has conducted more than 100 such workshops around the country. The title of his today's talk is Continuous Flow Process, a New Paradigm in Process Intensification for Functional Materials.
Thank you.
Please, Professor.
Thank you for the kind introduction and good morning, and we'll learn something about the flow chemistry or the continuous production today. So I kept my talk more in informal way. So half the talk is more as a tutorial seminar and then I'll show some results. The results are not that important. Let's focus on learning in the first half and then look into some of the things which I'm going to present are my personal beliefs, and I hope you agree with that, but that's, you can also have your personal beliefs. So I feel the chemical manufacturing or the way we practice science is changing very fast. And lot of us are not really changing that fast, and we keep blaming that jobs are being taken away, AI is going to take away everything and so on and so forth. It's not going to take away, it just requires a different skill. Okay, so if you don't adapt to the changing skills, jobs will be there, but you will not get them. Okay, so I don't believe that jobs will be taken away. It just as the time changes, you need to learn new skills. And because we are living in this fast changing world, within our lifetime, you can have multiple transitions. And that's going to be very important, to be flexible and to be agile, to just quickly change that. So nothing we can't replace humans. So that's still going to be there. In terms of chemistry, you will need chemists who can think, but the era of chemists who can only do certain reaction is gone and is going very fast. So a lot of chemists can do certain, like you have organizations where the team who can expertise in butyl lithium or Grignards and so on and so forth. And they'll continue to do the same reaction over and over again, and they can do that safely, and so those eras have gone because that will be taken over by machines. But you still need somebody to think of interesting chemistry. So AI and ML, because now organic chemistry is 300-year-old now, so a lot of data has been generated, which means now data is so large that you really can't comprehend and understand the whole thing. Which means now you need to bring model to harvest the data and then put them together for some concrete use, okay? And then you can come out with the models will predict it, take it with lot of salt what models predicted. It's good if your domain is defined and you're looking for shortcuts, but do remember in this shortcut you might miss something which is very critical. So experiments are not going to be replaced by it, but it can assist you in doing experiments in a better fashion. Both R&D and manufacturing is changing very fast, and organic chemistry labs need to adapt to this changing environment, and most of them are not really adapting to that. But sooner or later that will become very important. You need to bring automation and sustainability. There is no question about it. If anybody who is working with automation and brings sustainability in your business model, they will survive long, okay? So there's no charity nowadays, okay, you put the license Raj, only 3 industries can work and 4th will not come and 5th will not come. Resources are unlimited. Skills are really not that available. So if somebody comes out with a new skill, a new method or a new technology, there are enough resources available to take it forward very fast. Continuous production is required. It's been practiced for food and petrochemical and oil industries. Now fine chemical need to practice this. We are only dealing with chemistry where electrons are moving, and if electrons are moving, why do you need chemicals to give those electrons? Can you take, the electron doesn't care whether it's coming from a chemical or from an electric current. It's an electron. It has the same property. Can you take that using current, light, and then another thing is the chemistry what we have learned and what we have been doing is all in the flask, do up to 100, 120 degree, 150 degree, and that's passe now. What happens to your solution phase chemistry at 400 and 500 degrees centigrades? So imagine all your solution phase chemistry is up to 100, 110. Suddenly now you have access to all the way to 500 or 600 degrees centigrade. So the type of chemistry which happens there are completely different. They're still solution phase. And that can give you new leads and new ways to do chemistry. And the processes need to be continuous, either flow or mechano. Mechanochemistry is picking up very nicely, and we'll look into that. This is what I call now future of organic chemistry. This is with just one machine sitting there, and you can do high throughput synthesis, you can design. Now even softwares are available which can give you retrosynthesis, okay? And these softwares are improving by the day. So you can have softwares where you can write down your target molecule. It will screen through, so you have approaches, you can screen through all the literature available, look into many methods by which it can be made. It will give you the tree of making it. It will give you the source of the raw material, it will give you the cost and the safety and everything involved in that in a single shot, okay? And you have multiple ways to make that, and that software will do that. You decide based on your locality or based on the business model you have what you want to do, and then port that on a machine, and the machine will just duplicate it. Then you can generate all types of structures which are variant of that machine will do. Then you do screening of those. Once you know the screening is done, then you say this molecule is what looks potential. Then you go back to the machine will give you few kilograms of this. Then you do your further studies, and once it's done, you're ready for production, and then you again look for the assisted synthesis of productions. So that's what's going to happen, and there are many versions are available where footprint is very small and all types of chemistry can be done fully automated and using very few ml of the reagents. Give you one example, Merck, and many have come now where you do high throughput, completely automated synthesis. So let's say you decide that you want to do this type of coupling reaction You have all the ligands, all the base, all the solvents, and all the substituent to screen through. You just set up the whole system, go back, let the machine do it, complete separation analysis and feedback to the system. They can do 5,000 plus reactions in 3 days. It's not only the reaction, the next day you come, you get everything, a complete plot of every combination of reaction in terms of yield, output, and whatever you define the output. It'll take a large team almost a year to complete this type of work, and this can be done in 3 days now. And it requires all types of skill, instrumentation skill, automation, interfacing, chemists, and so on and so forth. And that's the pace at which things are going, because time is money, and that's how the businesses will go look into that. Sustainability, you need to bring in, whether you like it or not, that needs to bring in, but it's been word which is abused quite often than used, okay? You need to look into complete life cycle analysis, okay? It's just not that you took one process and one particular subpart and then say you can do that. Like you look at EV vehicles, look into lithium, look into what happens to a lithium post dates, what happens to a lithium where you're going to source it, and what happens to all the modules, all the energy which goes into making these batteries and everything else. So everything has to look into that. Mostly I see this abuse in the terms of bioresources. Anything to do with food or corn or everything, they say it's renewable. It's renewable, but is it practical and economical? Okay. And right now you can say, okay, I can make it from ethanol or a sugar, and you can do that, but that's the day you start using that at the volume you required, none of these things are viable, because whole thing will be shifted towards chemical production. What happens to the food? You really can't do much over there. So it's better to think directly now and look into biotech approaches where you can design the systems there which can keep on churning out this through fermentation or through bacteria culture or all those things, rather than looking at food as the source of that. You can think of waste as a source, but that's not going to value add, it's going to decrease the value. And lot of people say from waste we can use that one. Again, all the calculations are based on that waste is free. Okay, do remember, nothing is free. It's free till there's no use to that. The day there is going to be use, the waste will start putting the value to that, and your economic model will go. So if you're looking at really applied, you better start looking into all these features at the early stages. I see a lot of people say silica they use, it's a green silica from rice husk, but that's been there for long now. Suddenly, that's the main source of silica. Now they're using buzzword, it's called green silica, and then keep on doing it. You can get 1 or 2 publications, but you want to go beyond that, you need to really be self-critical and look into that. If you want to survive, you need to learn the anti-fragility rules. It's very interesting. I advise everybody to read the work of Nassim Taleb. It's an amazing author. He just talks. It's nothing to do with chemistry, just to do with lifestyle. And his thoughts are very confusing. So when you read that initially, you will feel that that's really stupid. But when you go deep and read it many times, you will realize how valuable these things. So these are his thoughts. Do hard things. Keep doing things which are harder and harder so that you really get and do things. Be adventurous. Don't believe in certainty. Certainty is going to be sure recipe for disaster, because you are not prepared when this is going to fail. And if everything works, you get up in the morning, everything goes as per the plan, nothing happens, life is boring. Embrace uncertainty, because that prepares you for a lot of things. Anti-education, this is what I keep telling. Our education does not teach us how to fail. It only rewards success. Every time they tell if you don't get 80 or 90 or now 99% marks, just not good. Failure is not good. But failure is the first step towards learning anything. Okay? Somehow as a society, we are teaching not to fail. Okay, that's somehow we need to teach how the students at the early stages fail, nothing wrong in that, and then move on. It even happens in IIT. We had a discussion last time. Some students want to do courses in, minor courses in chemistry, and chemistry department came out with, oh, you need to have CGPA 8, you should not have any course failed before that. I said, why? If they have failed it, they have learned their lesson, now they should be encouraged to do that. But somehow we have the habit, failure is not taken. And science is a philosophy. You need to learn by doing it. You cannot learn. Lot of us teach science as rule number 1, rule number 2, rule number 3. Believe me, there are no rules in science. If somebody says electron has a negative charge, that's not a rule. It's a hypothesis. There are two charges, one is negative, one is positive. You put electron negative, proton will become positive. Thomson has said this is positive and that is negative. So don't get bogged down by rules the way we teach it. It's a philosophy, and philosophy will only happen when you see, enjoy, and do things. So do learn by doing it, and somehow we don't teach that. So education is important to a certain extent, but don't get stuck only with education. And you need to have anti-fragile lifestyle. Every day you should say, tomorrow is going to be disaster in the night. What will happen if everything just shuts down in the night? What will I do in the morning? And if you can sleep, get up in the morning and start your lifestyle again. And I keep telling people, think that you have written off all your money. Bank has gone bankrupt, filed for bankruptcy and lost everything. What happens? Don't jump out of the building now. You have to still get up in the morning. So prepare for failures. Okay? Whatever worst can happen, imagine that. Okay? The day you fail is because of your imagination. If you don't have a plan for the plan which does not go as per the plan, you're doomed to fail someday. Okay? So make sure, prepare for this uncertainty, and that will help you. Choose right chemistry, as I told you. It's becoming very, very promising now. Electro-organic synthesis, which was there in the early century, now it's been picked up again. The reason it was not picked up is because you couldn't scale up a batch reactor, which is electro-organic synthesis, because you will not have the communication beyond few millimeters. Now with the flow chemistry, this is becoming very, very popular. Photo flow is also there, but still more of a jugaad. The scale up is not there, but this is quite nicely scaled up now. And look into chemistry in new space. You need to use the right process. There is no choice whether you want to, so it has to be continuous, and it has to be scalable, and it should be which a chemist can do. Okay? Because at the end, learning chemistry takes years. So chemists are the one who will do the first reaction, and then if you can take it and scale it up using a process, so the technology has come to the user, now the user. So what we do is we develop the chemistry and then transfer it to the process engineers and so forth. So those days are gone. A chemist can take it up and go all the way. So we believe flow chemistry and continuous mechanochemistry. Lot of us have the habit of any reaction, first thing is to use solvent. It's really not required. If you know the purpose of solvent, it's a medium to take the heat out or to dissolve. If your reactions are not really exothermic, why worry about solvent or a heat transfer medium? So a lot of reactions we try, we just dump the two things, and this is belief we have that solid won't react. That's another issue. But just mix it, grind it, put it in some agitator, you will see a lot of things happening. And till date, whatever reaction we try, we get some interesting results out of that. We have not failed in that. So if you, again the same thing, don't believe what you learn is the final word, and look into that, you will do very well. This is again very, very important, and I am developing a course to teach this one. Kinetic analysis, understand your process completely. In early eras, 40, 50 years back, kinetic analysis was extremely difficult because you have to do large number of reactions and you have to do with large excess of one, so that you can pseudo kinetics, you get with orders with respect to one, then second, then third, and then fourth. That whole used to become a PhD problem. Thanks to the development in data science, and for all those, all the slides are available here. I'm just leaving it here. That's the reason I use that computer, so that you can just take the copy from here. Absolutely not a problem. There's no secret when I discuss anything. So these two guys, Donna Blackman from Scripps and Jordi Bures from Manchester. Jordi was the postdoc with Donna, and they have come out with very interesting and very beautiful, simple concept. You do your reaction, just manipulate the data in a different way, and you can generate every type of reaction kinetic analysis of any reaction in the exact reaction condition which you are going to practice. It's not under pseudo conditions, okay? So the two approaches, you have start with a different starting point, you keep everything else same, just one reagent you change by, let's say instead of using 1 molar, use 0.95 molar, that's enough. Don't go from 1 to 100, no, that's not required. You can change the catalyst, or you can start with adding one more reagent, 10% of that, any one of the experiment. So you need to do only 2 experiments. One experiment which you are doing, and you want to get the rate with respect to A, decrease the 10% concentration or increase the 10% concentration. That's it. And do the same reaction again. You can follow the progress of the reaction, where rate as a function of the progress you are doing it, that's called reaction progress kinetic analysis. Jordi did postdoc with Donna and then came back and then said, there's even simpler way. Instead of doing the reaction progress, you just do the time as a variable. And he came out with an interesting equation. If you have done your Michael-Menten kinetics in your enzyme analysis, it's an extension of that, but a beautiful extension of that. So he takes every other variable as a time domain. So you get a linear exponential decay on this, and then the 2 different condition overlap of that. You keep on varying this order parameter. They will only overlap when the order parameter is the one which experiment is following. So, and as an excellent tutorial is available on YouTube. So please go just search Jordi Bures VTNA on YouTube. You will get an excellent tutorial with all the data available. And now as a chemist, you should be doing kinetic analysis of everything. And once you know order of the reaction, importance of each reagent, how this each is cross-talking to each other, how the catalyst is getting, lot of us believe the catalyst is 1 molar to 10 molar and or 1 millimolar to 10 millimolar concentration, but there are a lot of issues now they have discovered that even the catalyst concentration in certain region only works and other times it doesn't work. All these understanding you can very easy, even catalyst poisoning or catalyst activation through some reagents, all this can be studied in a single step. And that's very powerful, and this kinetic analysis need to be done to do that. And the reason it is not, this is where because you are sitting at the interface. And no offense to chemical engineers, they are very used to of scaling it up through continuous flow for hundreds of years. But there's a difference between volume scaling up and a reaction intensification. So a lot of these people, chemical engineers, have taken this so-called flow reactions developed through this approach, which are intensified reaction. See, earlier what they have done is they have taken a process and they have scaled up the volumes in food and oil industries. That's not an intensification, that's scale up. So they think continuous is scale up. What I'm saying is continuous is not only scale up, it's intensified also. And if you intensify a reaction and use the same engineering tools which you have learned, first thing they say is, anyway continuous we know for 100 years, what are you telling us new? That sets in arrogance, and then they take an intensified reaction and just do that and land up. Many accidents have happened, and this needs to be seriously look into that. Don't just convert an intensified reaction into continuous. You need to learn the tricks and the rules and do's and don'ts of this, and then only do that. In fact, one of our last article when we wrote in OPRD, we use sodium hydride in DMF, okay? And then again the referee said everything went all right, the editor came back and said, we will not publish this. There is no way safety requirement will allow anybody to use sodium hydride in DMF. Without reaction itself over time it becomes unstable, and there are many accidents have been reported. So then I told the editor that okay, that's the exact purpose, because with flow you can avoid this. Then he said, no, doesn't matter flow or no flow, this is going to have the same problem because you're still storing sodium hydride in DMF. And there are enough accident happen. So we wrote a whole paragraph about the why accident happens when people misuse the flow, take an intensified reaction and use the traditional knowledge of flow and just do that. Connect tubes and start doing intensified reactions. And that needs to be looked into that. So you need to learn the tricks of both of this, and this is a new domain. Don't just use the existing knowledge from here. And that's the reason now chemistry is difficult to learn, but we call this tooling is easier to do. So it's like learning to drive car. So you don't need to be an automobile engineer, you can still drive it. So these now tools have been developed in a technological way where they become plug and play. So a chemist can use it and understand these tools and start developing the production. And this is a stage where chemists now can take it. So when you look at process intensification, there are 12 rules or whatever you do. The best is if you can improve the throughput of the reaction, keeping safety and everything in place, you will do a process intensification. As we have already said, a reaction is nothing but breaking and forming a chemical bond. You are taking the electrons away. That should happen in femtosecond because that's your electronic vibrations and rotational motion. If that happens, all the reaction should happen in femtosecond. And there's nothing wrong with this chemistry. Reaction should happen in femtosecond. And imagine you start doing the reaction in femtosecond, and instead of one molecule now, you are reacting large number of molecules. With large number of molecules react in femtosecond, you need to take that heat out. And if you don't take that heat out, it's going to lead to an explosion. Okay. So what's happening? Reaction should ideally happen here, and we do the reaction over here. And the reason for this is, we can't take heat out. The technology has a problem, because the technology what we use, you can take heat out only from the surface. So any reactor and any utility setup you have, you just calculate how much is your heat extraction ability. You get X joules per hour as the heat you can take out. You make sure you generate less than X joule per hour heat. And when you generate less than X joule per hour heat, you back calculate your rate of the reaction. How fast can you do the reaction? Because reaction rate is generating the heat. So if you can generate only X joules per hour, you make sure your reaction rate is such that you don't generate that much heat per hour. And when you do this calculation, simple mathematical calculation, you turn out that all your reaction need to be done in hours and days time scale. And that became the norm. So every chemist will start the reaction, they all assume it's going to be 6 hours or 8 hours. So what they do is mix everything, stir it and go for tea and come back, or lunch, or overnight stirring at room temperature is classical case of chemistry. Chemists are very poor in documenting their reactions. Sorry, I'm also a chemist. We have no idea about rate of stirring. We have no idea about head space. And surface area to the volume, anyway, never heard of it. So we always do the reaction in the small flask with a stirrer which is rotating at 3000 RPM and a 40 mm of head space. You have only 10 ml of reaction. Every day it works in half an hour. And then it goes for production, and the process chemists and engineers come and they say taking 10 hours or 5 days to do. They say, I don't know what this engineers smoke. Come to lab, I'll show you every day this reaction happens in 1 hour. But they don't realize when you go to the plant, the best stirrers will rotate only 100 and 200 RPM. Okay, and the surface of the volume has changed. So even if the reaction can happen, their surface area is so small, you can't take that heat out. Okay, so this need to understand this. So how do you, so last 200, 300 of organic chemistries, how do you slow down the reaction? Okay, and when you slow down, you get selectivity, and you sell those papers as selectivity rather than slowing it down the reaction, and new chemistry gets developed through that. So you add solvent. Remember your Arrhenius equation. Most of us forget Arrhenius equation. Arrhenius equation is the best equation for a person to work. It just relates your rate of the reaction proportional to A and E raised to minus E upon RT. That you say as a activation energy, and everybody forgets A. What is A? Is a constant. What constant? We don't know, but it's a constant. A is not a constant. Rate of the reaction, if you go back to your transition state theory, is the number of effective collision multiplied by the fraction of molecules have activation energy. So at any given time, if you see an enhancement in rate of the reaction, one of these factors you need to explain it based on that. If you can't explain based on this, don't call it a magical effect. And that has happened if you look at microwave chemistry. So it's as simple as that. Every enhancement on the rate of the reaction has to be either effective collisions have increased or activation energy, then fraction of molecules have activation energy increased. 30 plus years of microwave chemistry, everybody said it's a microwave effect. Everybody forgot that it has to be one of these two effects. And none of these they could explain, and they kept on saying it's a microwave effect. And now everybody has agreed that's nothing microwave effect, it's a pure thermal effect, which means you are measuring the bulk temperature of the system in a microwave reactor. You can't measure molecular temperature. And there are fraction of molecules which get very heated. Their temperature goes high, the reaction happens, they come back, another fraction gets heated, and at any given time you have 1% of the molecules which are at very high temperature, 99% of not. And remember, the reaction is femtosecond. Yes? So even if 1% or 2% of the molecules are at that temperature, you will say immediately they will lose the heat to the surrounding, isn't it? But that immediate, it can be millisecond, microsecond, and nanosecond. But your temperature profile access to that is femtosecond. And slowly you see the whole reaction happens in few minutes, and then you say it's a microwave effect. Because there's no energy to explain in terms of this. Now it looks very easy. And that's why the hindsight bias is, we are all very intelligent when something is explained, and that becomes a pure science. So now I hope you will know why we are practicing it here. It's not just we want to do it. And as a chemist, you can feel happy, oh, it's not my problem now. It's a problem of technology, but that doesn't help anybody. At the end of that, it's our problem, we need to solve it. And we need to do, can we do fast and ultra fast reactions? And the current state of the art is now we are at milli and microsecond time domain. It looks very interesting that you are operating at millisecond, but do note that we are little better than the traditional chemists, but we are equally bad. We still are 10 orders away from where the reaction will happen. Maybe a few generations down the line, technology will come which will allow these reactions to be done at that. And of course, when you do the reaction fast, lot of things changes. So everything turns out to be economics, safety, and everything, and that everything is changing so fast, not in terms of doing the chemistry, even the understanding of chemistry is changing very fast, which we are not realizing. Okay. And another thing is, all what you have learned in chemistry, and I'll give you a few examples. Again, as I told you, science is a hypothesis. We'll treat that as a rule. Oh, my compound, I can't heat more than 110 degrees, it will decompose. That's the first thing any pharma project you do. Sir, everything is okay, but don't take it above 110. Everybody has forgotten about the kinetics, and all understanding is based on your batch technology. And they think that's a science and that's a rule. No. That's just over the period of the time it happens again and again and again. You start believing that's the rule of chemistry. They are not rule of the chemistry, they evolved from the technology. So when you do a flow process or any other process which is ultra fast, it is not the same process which you were doing earlier, which was happening in ours. It's a completely new process. When it's a completely new process, you better understand this as a new baby, rather than just taking the traditional knowledge and then acting on that. So all our experience tells us that these are new processes, not the same chemistry we can apply that. We have enough examples where you can heat systems, where 110 they say it decomposes, and we have taken to 200, 300, nothing happens, because the time they have completely forgotten. So we heat at 200 for 10 seconds, they will keep at 120 degree for 2 days. And that just completely changes the kinetics. One example I'll give you, retrosynthesis is changing very, 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 very fast, and organic chemists need to take note of it. This is a standard reaction. If somebody tells you we have to do this reaction, immediately they will say, no, this reaction, the issue with this reaction is the moment you generate an anion over here, it will undergo Fry's anion rearrangement and electrophile will attack. You will get this. So if you have to make this directly in one step, that's not going to happen. You need to go through 2 steps, or you need to protect it, because otherwise this anion Fry's rearrangement will happen. And then you say, why that will happen? They say it's an intramolecular reaction, and once is an intermolecular reaction. An intramolecular reaction always supersedes an intermolecular reaction. That's the first thing we teach in undergraduate courses. But that's again based on the knowledge, it's not the science, it's based on the batch knowledge, where the diffusions are all much longer, and when mixing is very small, your intermolecular reaction will always be slower than intramolecular reaction. Does not matter what the rate of the two processes are. And based on that, we made it as a rule. And Professor Yoshida and Kim, they came out with this interesting reactor where they do all the simulation and made a reactor where the rate of mixing is in nanoseconds. Okay, rate of mixing is very fast. Once rate of mixing is very fast, then the reaction pathway will be decided by the reactivity, not by mixing. And in this reactor, the total volume was this and around 330 microsecond. With this reactor, they could get 91% of the product, which was an intermolecular reaction happen when an intramolecular pathway was present. So amazing chemistry which they done. And this whole volume is this. They made all this compound reasonable yield. And at the end we say 25 nanoliter reactor, what are you going to do with any realistic? Again the same issue comes in. For a chemist, bigger the better. If I have a bigger flask, I am more better chemist. Because everything happening anyway 18 hours and 24 hours. We completely forget that throughput is volume multiplied by time. Since our times have been so large over last 3 centuries, we completely ignore the time, we worry about the volume. Now if you look at volume into time, and if this reactor goes on for 1 hour with 67%, you get 5.3 grams. That's quite substantial for any reaction. And if an engineer can design this reactor in 10 ml, you will get 2.1 tons per hour of your production. Okay. So imagine a 10 ml reactor, put it in your pocket, go set up somewhere and your production is ready for 2.1 tons per hour. And the best part of this is the safety. If anything goes wrong, your reactor will have a feedback mechanism to the pumps. Pumps will stop. You worry about what do you do with this 10 ml of reagent to dispose it off. And now you can think of your explosion-proof reactors putting in the cabinets. You can do the production in a big city. The problem is you require larger plants because for a batch technology, cost comes down with volume. And larger the plant you require, larger the manpower you required. And larger the manpower required, after you plant set up outside, the city develops around it. And then something goes wrong, regulator will say you get lost. City will not go, you guys close down and go somewhere wherever you want. Okay. But with this technology now you can do things wherever you want. We do hydrogenation in our office without changing a socket at 100 degree and 500 degrees, 100 bar and 500 degree. Because we generate hydrogen in one reactor, use it in other, and any time what we have is half a gram of hydrogen. We can just release it in open after the reaction is done. So things are changing very fast and that needs to change. And as told you, now if you can trap this intermediate and you can do both kinetic versus thermodynamic, you decide you want kinetic or you let it go, you get a thermodynamic product. And when all these things happen, and if you look at carbocation rearrangements, there are large number of rearrangements happen in your terpene and alkaloid chemistries. And if you can get the product from each of these intermediate carbocation by doing time result synthesis, your scope for doing synthesis completely changes and all your retro routes will change. And there are many such examples which are known. Hazardous flow chemistry, as I told you, you couple the two reactors and you can do all types of hydrogenation, phosgene, phenylisocyanide, all chemistry now can be done in a scalable fashion through this. As I told you, this is your solution phase chemistry, and this is where you operate on a flow chemistry because there are no seals and other things, no moving parts, so you can go very high temperatures. And I hope you remember your Clausius-Clapeyron equation. As the pressure increases, your boiling point changes to a certain before it hits the supercritical state. So you can do solution phase chemistry below the supercritical state, which for a given solvent can be 300, 400, 500 depending on what you choose. Case of this, you can use this nitrile from the acetonitrile now. And there are many such cases, and my classical is take all your source of starting material, that's what we do in the lab, dump them all together, put it in a hydrothermal reactor, which all material chemists have it now, which costs only 300 rupees. Each one of you have a furnace in the lab. Just put that together, put it in a furnace, let it cook, and you isolate it, you'll have few tens of compounds will be there, and then you separate them and characterize them, you'll have very new, many new chemical entity. And that's the reason I was telling, we need these old chemists of natural product extraction, because they were the champion of separating hundreds of compounds, characterizing it. And I firmly believe that if you put nitrogen source, sulfur source, carbon source, put it together and just put it in your hydrothermal reactor and just heat it, you will get few tens of compound. If you can separate, isolate and characterize it, you will have new chemical entities, new heterocycles which doesn't exist now. And if anything you find them interesting, then as a chemist you repeat this and scale it up through flow and optimize the product through that. So doing new chemical entity search, this is the way to go. Give few examples. Butyl lithium, we say we transfer heat very fast. Typically then if you have done butyl lithium, -78, dropwise addition. We do at 15 degree at 100 liters or 100 kg per hour. You can now back calculate the cost. And anything goes wrong, you are looking at a small volume which you can deal with. Of course, there are a lot of other safety and other features have to be done, but it is doable, it's been practiced. My favorite is this, agrochemical, 10,000 tons per annum of this chemical, Chinese company, decided to try flow reactors. This was made with 20 batch reactor, each one was 25,000 liter. So you can imagine the whole plant was size of a city. They tried this Miprova reactor from Alfeld. Finally, in 6 to 7 months, they could finish the project and set up this reactor. And this is 7 meter long, and it is 1.25 meter dia, 1.25 feet dia. You can see the car in the background. And this whole reactor produced the same amount what that 25 KL 20 reactors were producing. And they were so excited that they like this whole technology. They have hundreds of chemicals and hundreds of agrochemical companies. They just bought over the Alfeld. So overnight the Alfeld company became the Chinese company, and now that's what they're doing it. We also have set up the state-of-the-art lab where we take anything from microgram optimization and take it all the way to few 100,000 liters per hour. It looks very impressive, but remember we are chemists. I'm even not a chemist, I'm a polymer chemist, not even an organic chemist. So it is doable. What I'm trying to tell you is it is doable. Believe in yourself, you decide that you are not, and we failed, we did so many mistakes. And the reason we could learn is we could afford to do mistakes. We had large amount of funding from another project, which we diverted here, and we kept on doing mistakes, we kept on learning, and we just got so lucky after a few years. We just knew every mistake what can be done. We developed the whole platform around it to avoid these mistakes, and we just had a unique character now of system. We work with all the industries because we feel that's the future is going to be there. All these industries we have trained, worked and associated with us. Give you a few glimpses before I close it. What type of chemistry other than the industrial chemistry, which we can't discuss much. We keep doing a lot of blue sky research also through flow, and that's what I'll show you. So earlier the whole thing started with this conducting polymer, and I'm a strong believer that hard work alone does not pay off. You need to be lucky. And luck only favors who are prepared mind. It just doesn't favor anybody. You can't just sleep. I keep telling, if you have a dream, the first thing to do is wake up and start working on it. You can't just keep sleeping and have dreams and then say dreams come true. No, that's not going to happen. So this is exactly the story, serendipity, how it happened. I wanted to scale up a P3HT which we made for photovoltaic application. I call a salesperson to buy a batch reactor which was 5 to 10 liter. Remember, you are in IIT academic lab, you work with flask. So I said, if I want to set up a good production setup, let's say get this a 5 or 10 liter an automated jacketed reactor. So I called Series, was pretty good that time. So called Dinesh Purohit, the salesperson of Series, a good friend of mine, was sitting across. And he said, sir, Series is developing something called flow reactors. I have no idea what are these. If you are interested in, I can put you in touch with that. That's like 2012 and 13. And I got interested in it. I spoke with them. I bought the reactor and realized I can't use it. And I kept on learning, and that was the transition point. If me and Dinesh would not have met, and if you would have said it, there's a batch reactor, Atlas and potassium, take it. He just mentioned flow reactor and life just changed completely. So be prepared, be ready to change, and things will just change. So anything alternate double and single bond, you can make conjugated polymer out of this. We focused on these three because these three were very important. The first we focused was on polyaniline, which are nanoparticle. The whole idea is, if you take a nanoparticle, initially they'll form nanoparticle, but if you scale it up, these nanoparticle will act as a seed and you get junk out of this, junk material, because that will act as a seed for the further growth. And that's the reason anytime you make nanoparticle, you keep your stirring very high and you keep your conversions low. So you get good quality nanoparticle. We said if that is the case, secondary nucleation can be prevented in flow because as it forms, it keeps moving forward. It will not see the starting point. So we don't have to worry about conversion. We should be getting same results at higher conversion also. And that's what we did for polyaniline. And that's what now typically in the literature, if you look at very low conversion, very low throughputs they do, and look at over throughputs, which we can do that. And this is how the whole setup is Toluen because it was precipitating on the wall. That's Karuna's work. She's sitting here. And then this. And extremely good reproducibility. We then take this, make a graphite ink, and then we print the supercap for organic electronics. And this we published it, and then we realized that toluene was a sacrificial solvent because we were preventing the deposition on the wall. And with the time as we progress, we came out with a new reactor where it can handle the slurry. And then we don't require the toluene. Now we can make few kgs per hour of this nanofibers. So any nanomaterial which requires scale up can be done through continuous flow. This was the first project for which we wanted a batch reactor. And that is the product which is commercially available, made through the batch reactor. We landed up in buying the flow reactor and started doing it flow, and we were successful. We got the material which looked like this. And remember I told you, there is no process which is the same when you do through flow which you have done through batch. We are completely new process domain, and we went there, we got this very interesting material, and anybody and everybody who sees it takes this material for device applications, and every year we keep getting publications out of it. Any material we make, we have a new material. Any reaction you do, you have a new domain to operate on that. So it's amazing. It's just the imagination and how much the student wants to do it can be done. We looked into color changing polymers. This was the standard synthesis. You take dimethoxythiophene, dibromodiol, you get this one, and then do dialkylation. That's been there for 30 years, and we wanted to scale up. Nobody has scaled up. When we were scaling this up, we realized few issues. When you do this reaction, you will have mono, di, and unreacted product. And all three have the same polarity. It's nightmare if you have 70% reaction to separate these three, and that was just not possible to scale up. We looked into that. If you have to scale up, you have to look into completely different approach. And we said, can we do this approach? Instead of doing this ring closing first, you do alkylation first by protect this through acetone. That's a quantitative reaction, acetone as a solvent. You put this, you get quantitative reaction very fast with silica sulfuric acid. Now you do the sodium hydride reaction, do alkylation. And when you cut this out, now you have compounds which are easily separable because polarity differences are very high. And anything which is unreacted, anyway will remain the solvent. Okay, it's an hydrocarbon, it's not an aromatic system. And this can be purified easily and coupled to this, and we did this. And the beauty of this scheme was every reaction can be optimized to 100% conversions with pure compounds. Can be pushed in because the flow is setups, and this is where the referee was saying you cannot use this technology because that's just not allowed. And then we explained to them, flow is the only way this technology can be used, and then we showed them the system where I can take sodium hydride as a solid feeder and alcohol as a liquid, and ICA and others are the small homogenizer where both can be fed. You mix the slurry and then you just send it to the reactor. And we're implementing it one or two places. There are a lot of reagents where reactivity changes with time. And you can use the solid liquid feed separate to do that solution to that. And we coupled all of them, and now there is no separation, anything in between. We get this product again and again, and we are now working with a new startup in Bombay to scale up these materials, and hopefully the first time we can scale up this and we'll be able to get some interesting results out of this. Mechanochemistry, I told you, we do any Diels-Alder reaction, aldol, whatever you do, you get something interesting. Mechanochemistry don't do extremely exothermic reactions, but anything else you can just, which is not highly exothermic, can we start doing it, and wonderful result comes. So we did this again. Remember P3 H2 through flow, suddenly you got very interesting. Now we do this polymer of P dots and pro dots through this, and we again get very, very interesting materials through this. And we are now exploring mechanochemistry for all type of work. Last 2 minutes on this emulsion polymerization. All your paints and adhesives are based on emulsion polymers. Emulsion polymer has its own mood in the sense it's a very dynamic process. Based on the surfactant, based on the size of your reactor, based on your monomer, based on the day, humidity, everything, the stirring speed, the final product which you are going to get paint is going to be different. And that's the reason you have so many companies, because everybody develops their own emulsion at a scale and have their own products. Because the dynamics from monomer to the polymer is huge and you can't control that. Another system is a mini emulsion where you think of kinetic emulsion, and if you can get the kinetic emulsion, they polymerize as it is without dynamics. In that case, you can have very good controls from start to the end. But kinetic systems can only be stable, remember, at a very low volumes, and is a kinetic, so it won't survive the moment you have little larger volume or little larger time. So we have been thinking, can we do a kinetic emulsion, scale up of that, and then do the polymerization from that? All these issues can be resolved. So it was just a blue sky thinking. We did set up, to cut the short story, long story short, we took two reactor. One was a spinning disk reactor, which is highly agitated, works at 400 mil per minute. It's a highly sheared system, the best shear system, and we are doing a lot of reaction in that. So we set up a loop with that, and we get a kinetic emulsion, which is now completely in recirculating with this. So it is stable over time, because it's getting regenerated again and again at 400 mil per minute. And then we take another feed out of this and put it in another flow reactor, and we polymerize that. So polymerization is 5 to 6 hours. Kinetic emulsion is generating into few milliseconds or microseconds, and you couple this to one sort of non-correlated system by combining these reactors, and we got very interesting results, and we could successfully do MMA polymerization, and we now do all this multiple times and we get the same system there. So there's no dynamics from start to the end. And this is the first example of a scalable mini emulsion polymerization, and we're excited that this will open up completely new domain for paints and formulations. And we can now control the particle size by changing the kinetic parameter, either by changing a little bit surfactant or a little bit of the RPMs on that. As I told you, there is no microwave effect. You can give us any reaction. Microwave is not scalable. And it's funny, there are still people who are selling you scalable microwave reactor, and people are still buying it. 1 kg is scalable, but that's not going to happen. Any reaction you give us, we know that it's a thermal effect. So if I have to get toluene to 250 degrees centigrade, you can get small molecules through microwave, but we can do that through flow. And anything we do that through flow, that's again Karuna's work. We took this KCC, this is the microwave results, and these are the flow results. We can match any system, and we can do better than that, because we have much better control. If the microwave gives you in 2 minutes, I'll give you in 2 seconds also. And I will give you scalable solutions to that. And that's the beauty of this process intensification. So I hope I'm in a position to convey that things are changing very fast. Most of these things can be learned. How to learn cannot be taught, that's the only problem. The motivation to learn has to come from you. At this age, I tell every student, learning is not a limitation at this age, because everything is available online. Okay, gone are the days where you need to go to IITs or MITs or Harvard or ETH to learn anything. All of these people have put their content easily available on the web page. You sniff through those. Learning is not a problem. But then nobody wants to learn. That's the problem. So make sure you develop the habit that every day pick up something new. Someday you'll pick up small, and soon you realize that you will learn quite a lot. And more you learn, more you are irreplaceable. Ask yourself, if tomorrow my organization has to remove 10% of the people, which will be I be? Will be I be 10% or 90%? If you're in 10%, you better prepare your bags right now itself, because that's going to happen. So make sure whether you're required to do something or not, do more than what you're required. Create dependence of your organization on you. The day your organization depends on you, your percentage shrinks in the favor, you will be the last one to be gone. Okay? And that can only come, nobody will tell you, your job duties are defined. Beyond that, you only have to put in, and that's not difficult nowadays. So I hope this will become the paradigm for both R&D and manufacturing. This is the current lab group which you work with. A lot of people will collaborate because we only have process guys. So we make process for everybody, whatever is interested in, and then do that. We were very lucky that we had a large project from Ministry of Information Technology on explosive sensor, and we have to develop and scale up of that. We use a lot of that scale up money to learn all the flow, and then flow paid off, and then it became a self-propelling system, and it's working very well. And I thank you, and I'll be happy to take any question which you have. And whole day I'm around here today. Yeah, thank you. And all the slides are available here. You can just have a copy of that. Yeah.
I think the continuous flow chemistry lab, basically you're talking about continuous learning.
Yeah, it's a continuous learning.
There is a good message. Just a specific question on the polyaniline. I see that it is a biphasic system. In our own experience on a project, we realized that there is this interfacial polymerization. Sometimes you'll have to be very slow. Rather than increasing the rate of reaction, you have to go slow. So, as a general philosophy, I wanted to know your thoughts on flow. If you have to slow down the reaction, it's an exact opposite of what you're trying to say. So, is there a strategy that we know, or is it something that we cannot?
Slowing down is easy. You change the concentration, but you are looking at interfaces.
Interfaces, yes.
Yeah, I will still look into flow as my interface, because what happens when you have a plug flow system and the two plugs are moving, your interface are continuously getting regenerated, because the valves will hold on to the liquid and the Milo will move fast.
Yes.
So that turbulence which you get is much better in the biphasic system. The reason we use biphasic was because we were having precipitated polymerization, and when the nanoparticle precipitate, they will precipitate on the wall. So to prevent that on the wall, we created droplets of aqueous system in toluene. And the polymerization happens in aqueous system, which was not really touching the wall.
Right.
So that was the reason we put it. But anything, I still feel no reason to slow it down. You might get better results through interfacial, through plug flow system of a two phases, because of this turbulence which gets created.
Contact time.
Limited contact time, and then it will regenerate with a new monomer, and you might get much better quality of the material. We have not tried interfacial polymerization through this.
Okay.
Maybe somebody should try that.
Other thing, Anil, is I think it's a big gap. There is a lot of knowledge on transition metal character in homogeneous phase. I generally see that is still an untapped area. We are talking, when we work on fixed bed systems, you have done a lot of work on fixed bed, good examples, but some of the asymmetric hydrogenation, homogeneous phase, is still something that catalysis has not been exploited so much in flow. There are examples.
It's a very inefficient way of doing homogeneous. So I will still work on converting that into heterogeneous. Because let's say you scale it up, separating will cost you so much money, and you can't let even PPB level of this metals into your final product. So we are working on a couple of projects where now homogeneous catalysis convert into heterogeneous, and current industry anyways 90+% is heterogeneous, but their reaction kinetics are very slow. So we enhance the kinetics by flow because our mass transfer, heat transfer are more. So give you an example, if you take a classical reaction, heterogeneous biphasic reaction, solid liquid, takes 18 hours in a batch reactor. Same concentration, same temperature, same everything, we finish that in 15 minutes because our heat and mass transfers are good. So we don't use fixed bed, we use that agitated one. So all that fluidized bed I can duplicate it without having a fluidized bed and scale it up without engineering intervention. So we take the best of fixed bed. So we optimize the catalyst through fixed bed because I can do screening very fast. Once it's done, we immediately shift to the slurry reaction because we don't want to develop fluidized bed. And we even the hydrogenation through now slurry reaction works beautifully. So homogeneous scaling up will be economically I think is going to be. Till there's no choice, then people do that. But the moment you develop a heterogeneous catalyst, that will go.
Yeah, thank you, Professor. I always, learn something new from your talks and very motivating to, hear you encourage others to take this up. So, I had one question. We're talking about all this process intensification, so more in general, not a specific case. So we are, accelerating reactions, having more collisions and all of that. Have you encountered a situation where the impurities are also, higher, and because we are sometimes saying that the purity profile is not as clean as a batch reaction.
I'm not
and
surprised.
that separation is actually more of a challenge.
Yeah.
So sometimes while we say that flow gives an advantage, we are finding that lower, because we have to have additional purification, it's a challenge downstream. So have you encountered
Yeah,
this?
so I never said
is
flow is advantage. I said flow is a new process window. So new can be not good for you. So you have to understand your process in this new domain. And chemists are very clever. So you'll see new impurities. But if you play around with these tools and the combination of time and other things and concentration, you should be in a position to, once you understand this, so every process has to be optimized in flow. But it gives you the ability to do it fast, which batch will not do it. So I keep telling there's no magic in science. You have to, at the end of the day, explain it. It's a new process. New impurities can come. But if your impurities are forming because you had a longer time at higher temperature, because typically I look at impurities form towards end of the reaction, where the conversions have become very slow, because 95% conversion, and the product is still staying there, like Friedel-Crafts alkylation. So the product has more chances of reacting because the 10% concentration is higher. That you can avoid through flow. So if you understand the two worlds, but you still have to optimize the process through flow, and some process may be just bad luck that you will not get it to the flow. So it's not a solution for all, but a good solution for few. You understand both sides, and if you can sort of get an idea about kinetics, and that's the reason I'm emphasizing everyone, go to those Donna Blackman and Jordi Boot's videos and papers. Same reaction anyway you are doing. Just put a IR or anything and you will get such kinetic information, because lot of these reactions in pharma are multi-step reactions done sequentially in a batch. And you have no idea when to add. This is all empirically derived with past. That will help you a lot if you get the kinetics understanding of that. You had something? Yeah. No chemistry question. No organic chemistry.
Wonderful talk. I want to go back to the Arrhenius equation because I will challenge you and Neil on the fact that this is a constant. It's a constant with dimensionality.
No, I never said it's a constant. I said it's a fraction of effective collision.
Okay, but this is like exactly what you said, because the entropy of the reaction is
Yeah.
A completely.
Ah. So A is not a constant. A is the fraction of, fraction of molecules, effective molecules, multiplied by the fraction of molecules which are activation energy is your rate of the reaction.
But for the younger
Yeah.
behind it, basically it's the same as the dimension as your rate law.
Rate law, yeah.
Do the rate law,
Yeah,
A is
A is required. But they think it's a constant. That's, so if you ask any undergraduate student, they say A is a pre-exponential factor. It's a, yeah,
maximum rate that you can
achieve, yeah.
Thank you for reminding everybody of this.
Hi sir, this is Jagan from Dr.
Yeah.
Reddy's. Thank you and for your inspirational talk. I have one question. This is in general from lab to plant rather than the batch process when we develop in the flow process. So to ensure the same design space what we are developing in the lab, there should not be any change with respect to the plant or scale up. So what could be the parameters to be considered? First of all, is it the flow is scale dependent?
No, so you use then interface reactors. So if you, let's say you are going for slurry scale-up, so start with reactors which are already been solved by engineers for scale-up. So you use an ATR or an AutoCAM, which all the engineering problems have been taken care. Beyond that, don't try to do and fabricate anything. So don't take a tube and then try to scale up, because that becomes a problem which engineering solutions are required.
Even considering the similar, as you said, the interface reactors, is any particular parameters or something to be
No,
looked
we
into or
are
something?
pretty close. So typically, let's say if I optimize my reaction in that ATR, and let's say ACR is the smallest one, which is 100 mil, and ATR, which is few liters, we are within 5% window of the final optimization.
Especially in homogeneous reactions, sir.
Homogeneous or heterogeneous? Homogeneous, why you want to go for ATR? It's not ATR. You can go to other. So if you are a homogeneous reaction, then go to the silicon carbide one. They have a scalable.
Yes.
And then you spinning disk. These are the only 3 technologies which are scalable right now.
Correct, but I am talking about in the same line. So the design space what we are working, developed in the lab, sometimes it may slightly shift in the plant.
It can change, but it just doesn't require too much time.
Talk like flow is a scale dependent, flow is not a scale dependent kind of thing. It is a
No, it's not scale independent, it's less scale sensitive, I will put it that way. Compared to a batch is a new baby. 100 liter reactor and you want to do 1000 liter reactor, you start ab initio again from very start. So flow is less sensitive to scale if you're using the right tools. So make sure your pumps don't have a pulsing flow when you go to higher flow rates. And if you use your peristatic pumps and others, that's not going to work. Make sure there's a mass flow controller in place, there's a feedback. Make sure before you set up your reactions, you calibrate the pumps. You can't assume that months after months they will work the same way. So if you take care of that, then variability is less here. That's what I say. But there is still variability will be there. Will be within that domain, yeah.
Okay, so please give a big hand for Professor Kumar's very informative non-organic chemistry talk. Please.
Thank you so much. So I request Professor Manojit Pal to kindly felicitate Professor Jerome and Professor Anil.
Oh, okay. It's not shared.
All the speakers.
Yeah, come, we can have a group speakers for the record.
Just to give a background, this is something called B3. It's a lot of metallurgy work native to this Hyderabad, Karnataka, Telangana region, where the silver is etched, and upon revealing the gold, you can see the silver.
Maybe they can remove the slide.
Yeah, slide पीछे ऑफ कर दीजिए.
Roll background.
ये ऑफ कर दीजिए प्रोजेक्टर.
Yeah, you are anyway always a speaker. Without you, how can we have a meeting? Please, sir.
You want to switch off the projector? Already.
Yeah.
Digital which comedy pictures.
In the meetings. In the first tea break is the time when all speakers are there, we get a chance to get a good photograph. In a
Sir, I also wish Professor Srinivas Harvanti to felicitate Professor Manoj Pal. Thank you so much. We will break for tea now and assemble back here within 15 minutes. They are in the auditorium, outside. Thank you.
I look at 4 oxygen parachuting and that's very closely connected. And it's stable.
Good afternoon to all. At the outset, I thank Dr. Srinivas for giving the opportunity to share some of the ongoing research activities in our department, that is Department of Catalysis and Fine Chemicals at Indian Institute of Chemical Technology. Thank you, Chairman, for introducing me to the audience. Here, I think the first lecture is a lot of chemistry, and the second lecture by Professor Anand, a lot of philosophy combined with flow. And I don't know where I fit in between. I'm not going to tell much chemistry, some of our own examples and how we are working in the continuous catalyte reactions relevant to the industry, and we are also working with industry on their problems. So maybe it is too elementary to all, but I thought I don't know that the audience who are there. So we know about the importance of the catalyst, how the activation energy how the catalyst is alters the rates of the reactions. But why the catalysis is so important? Because in the chemical industry, 80 to 85% processes uses catalyst in one way or another form. Either it may be homogeneous or heterogeneous or enzyme. Okay, so this catalysis is more important, particularly in the energy and fuel sector, where most of the petroleum industry uses the catalyst process. More than 90% of the processes used in the petroleum refinery or in the synthesis of bulk chemicals utilizes these catalysts. And of course, another one, as we know, the catalytic converter used in our cars and the pollution abatements. Now the CO2 and greenhouse gas emission control, also the catalysis is playing an important role in controlling this polluting greenhouse gases. So as we know, we have three catalysts. Maybe with catalysts, people talk homogeneous and heterogeneous. We know the advantages of disadvantages. Both have advantages and disadvantages. And heterogeneous, because I practice heterogeneous, I say the advantage of the heterogeneous catalyst, where you can use the solids and which you can readily separate it, or maybe it will contact and coat the product. So there is a less contamination, and there is no requirement for the separation from the products or reactants. So, but there is another disadvantage is compared to homogeneous, the selectivity and the rate of the reactions may be vary a bit less in terms of selectivities. Nevertheless, both have their own advantages and disadvantages, and we have been practicing the heterogeneous catalysis. And if you look at the heterogeneous catalysis, the advantage, either you can use in a batch process or in a continuous process. In the batch process, you can at the end of the reaction, you separate by filtration or some decantation, other things, and you will get the products. In the continuous, which is more advantageous, because where you fix the catalyst at certain location and you pass on your reactants, and the reaction is instantaneous, and then you will get the products. And whereas in the batch process, you require a certain time to have the required chemical reaction, bond breaking and bond forming. So, but when compared with the homogeneous, as I mentioned, in the continuous production, then you can have the high throughput and easy separation and no contamination, and you can have the recyclability. So catalysis, as I mentioned, it used mainly the heterogeneous catalyst. I mentioned it is in the petrochemical and petroleum refinery. Most of the processes used are in this one, and environmental production. And we know in our high school we studied about the ammonia synthesis, all is catalytic process. Okay, that whatever Haber process. And now it is getting importance in the pharma and agrochemical, where because of the environmental constraints, people are looking for the heterogeneous catalyst. Earlier, there was not much focus on the development of the heterogeneous catalyst for the synthesis of some of the fine and value-added chemicals. Now, stage came where now Professor told about the flow chemistry. Of course, when you have a fixed bed, he told first we do in the fixed bed, then after optimization of the catalyst, we can convert into the flow. So we can reduce the size of the heterogeneous catalyst using the flow chemistry also. And see, most of the products from the petroleum industry, whatever we get, the gasoline or this LPG, naphtha, everything, or all our monomers or solvents, chemicals, everything produces from the crude oil using the heterogeneous catalysis particularly. So now, as it is well established in the petroleum refinery for the synthesis of the bulk chemicals or the refinery product, can we utilize these heterogeneous heterogeneous catalyst for the synthesis of the fine chemicals? Now, either it may be batch or continuous. Of course, continuous is more advantageous when compared with the batch process, but because the fine chemicals there actually the activity depends on the how selectively you can convert into the water, because the volumes are less when compared to this petroleum. So the development of the catalyst for the synthesis of fine chemicals is a challenging aspect. So there are different types of reactors where you can do this heterogeneous catalysis. Either it may be a continuous tank reactor, it is more or less similar to that type of a batch reactor. And of course, you all know about the flow reactors. And that what we are mainly focusing today, I am going to talk where we are practicing is the fixed bed catalytic reactor. So where the catalyst is a solid, is fixed in a reactor, and the reactants are passed through the catalyst. Either the reactants may be liquids or gases, or they can be in the gas liquid form or in the vapor phase form. Or if you want to scale up this, instead of one for the heat transformation, we can have multiple tubes so that you can scale up this one. So and sometimes where you have a heat coefficient and where the contact is not that good, then we can use fluidized bed reactor also. In the petroleum, the fluid catalytic crack reactor where the naphtha is cracked utilizes this concept, and we are also started working in the fluidized bed. Similar to that of the fixed bed, but the catalyst will be moving. Okay, that is the only difference. So in the start-tank reaction, generally the heterogeneous catalyst may be in the powder form, but when it comes to the fixed bed, it should have a certain, because when the reactants are going through a catalyst bed, there will be a pressure drop and the temperature gradient. So for the passage of this one, the catalyst will be in the different shapes. Either it may be a granules or a tablet or a extruded or a honeycomb structure. Depending upon the nature of the reaction, either you are working in the liquid phase or in the gas phase, then we will have this heterogeneous catalyst in different shapes. So as I mentioned, when you do the heterogeneous catalysis in the continuous fixed bed reactor, these are the advantages you can always have, because it is a continuous instantaneous reaction. So depending upon the how much production you require in a given time, you can change the number of tubes of the reactor. So then you can get the high throughput, and it is mostly because there is no contamination of the active catalyst with the reactants or products, so you will have a cleaner synthesis, and because of this continuous flow, you have improved mass transfer limitation and less contaminations and less downstream, because separations and other things you can avoid, and easy of doing with the gas liquid reactions. In the batch, it may not be that efficient when you do with gas liquid reactions, and because of the continuous, it saves the time and also energy. So these are the advantages. Of course, there are disadvantages also when it comes to it depends on the reaction to reaction. So the heterogeneous catalyst in the maybe in the flow or in the fixed bed, they will be in different shapes. Generally now in the packed beds, where in the flow reactors, small reactors, they are using in the powder or particle shape, or you have a capillary channels, or they are there. But in the monoliths or honeycomb shapes, the structural catalyst they will use in different forms in the continuous fixed bed reactors. And now coming to the catalyst, the heterogeneous catalyst can be prepared by different ways. Generally, the catalyst, either in industry you practice palladium carbon for your hydrogenation reactions, or you do vanadium based catalyst for oxidation reactions. So these are all solid catalysts. Generally, if it is a metal, either it may be a noble metal or the other metals like nickel or copper, cobalt, or if it is oxides like vanadium pentoxide, or manganese or zirconia, titania, these oxides. And sometimes you take, generally for example, if you are dealing with the palladium carbon, so palladium is only 2 to 10% and rest is carbon is inert. So that means you have a support, and the active catalyst is dispersed on the almost inert support. Of course, supports also play an important role. And so for this preparation you have impregnation method, co-precipitation method, hydrothermal method, and also we use zeolites. Zeolites are nothing but silica aluminates. So there you can prepare by the hydrothermal method. And chemical vapor deposition or flame, depending upon what precursors you are taking. Either generally we take metal salts to prepare the oxides, so then we do the precipitation with a base so that we will get hydroxide, and then we calcine it, then we end up with the oxide. So and so different catalysts are known because this like alumina, silica, iron, copper, zinc, and titanium silicates, and polyoxometalates, ion exchange resins, recently metal organic frameworks. So a lot of activated carbons, a lot of catalysts are being developed depending upon the nature of the reaction and what reaction you are looking at. So we are also working on the synthesis of different catalysts for our applications. So if you see the heterogeneous catalyst, how actually the 4 steps are involved in a heterogeneous catalyst. The first one is because the reactants has to adsorb. Either at least if there are 2 reactants, at least 1 reactant should adsorb. Okay, there is a kinetics are reported. If 2 are adsorbed, that is called Langmuir-Inshelwood mechanism. There is a Rayleigh-Inshelwood mechanism. So the reactants adsorb on the catalyst site and they undergo the bond breaking and bar formation. They are intermediates. Then the product, the reactant has to be dissolved from the surface of the catalyst. So it is a all surface reaction. So that's why it is instantaneous. It occurs so fast. And that means adsorption and activation of these reactants, and then diffusion of the products from the surface. It always done in the, because it is a continuous process, so this is very fast. So as I mentioned, we work mainly in our IICT, we are working on solid acid and solid base catalyst. For depending upon this one, we are taking a lot of oxides, particularly if it was oxidation, we work on vanadium, manganese, cobalt systems, and if it is a solid base, we work on magnesium, strontium or hydrotalcide systems, and if it is metals, we take generally zirconia or titania or carbon as supports for palladium, platinum catalysts. And actually, when you look at the activity of the catalyst, as I mentioned, the 4 steps, actually the catalyst also have different these things. One is how efficiently it absorbs on the site and how the bond breaking and bond formation is taking place. Of course, those are influenced by the reaction conditions. Apart from the reaction conditions, the distribution of the active component and the role of the support and the properties of the supports also influence the overall activity of a given catalyst. So that's why once we prepare the catalyst, we thoroughly understand its characteristics. So we do a lot of characterization techniques where to understand what is the size of your active sites and how they are distributed. Because for example, you have taken in one reaction, if you say 5% palladium you are making and 2% palladium is also giving same activity or better activity, because if you make a catalyst in a different method where you can disperse the palladium more efficiently than the other method, so even 2% palladium itself sufficient to do the same reaction. So that all depends on the method of your preparation and the property of the support and so how the metal is interacting with the support. All these will influence. So the catalyst preparation sometimes says it is not a chemistry, it is a art. So of course chemistry with art, you can make the efficient catalytic systems by adopting different preparation methods. So having a brief introduction about the heterogeneous catalysis, and I am coming what we are doing at IICT. So we are working on different reactions where we are using this heterogeneous catalyst. We are working on oxidation, amoxidation, oxychlorination, hydrogenation, aromatization. Of course, now this is the very important area where the heterogeneous catalysis is playing, where the green hydrogen production or blue hydrogen production and carbon dioxide utilization, converting, using as a C1 source to convert into methanol or dimethyl ether or formic acid, or biomass, which is an alternative source to the fossil fuels, where this carbon, hydrogen, oxygen bonds can be converted into different chemicals or fuels or fuel additives. So these are the activities where we have expertise in the design of and synthesis of these heterogeneous catalysts. And we can evaluate these catalysts in batch reactions or in continuous reactions, that is fixed bed, and we have we do thorough understanding about the catalyst by various characterizations, and we have the ability to do all sorts of reactions from the room temperature to as high temperature as 800 degrees and at atmospheric pressure to up to around 50 to 60 bar pressure. So, and we also have the upscaling facility also, and we have the expertise in doing these type of reactions. So these are the sum of for the benefit of others who are not much. So this is all continuous reaction where you have a reactor in that, and it is the temperature is controlled and the flows are controlled with mass flow controllers or rotameters, and then you can have the heat exchangers or the condensers and the gas liquid separators and the product analysis. So we have autoclaves also, and we have the fluidized bed reactor, and we have lab scale to bin scale where we can do different reactions from. We do, if it is a small scale, if the temperature is not more than 350, then we will do in even glass reactor where you can see the catalyst while doing the evaluation. So after preparation, we do characterization with different techniques. We have a operando Raman spectroscopy where even it is a gas phase reaction. During the reaction, how the catalyst characteristics or phase changes we can do with this FTIR and Raman spectroscopy, and we do surface area analysis and acid base properties and all we can do, and to understand the structure activity relation, which is very important in the development of the heterogeneous catalyst for a given reaction. So having this these are the actual catalytic systems we are working in our IICT. We are working on zeolites, heteropoly acids, metal, mixed metal oxides, hydrotalicides, supported metal oxides, and carbon from the waste biomass. And also we are working on the noble metal catalyst and also carbon, nitrogen doped carbons where we use a non-noble metal catalyst for different hydrogenation reactions. So we have expertise in preparation of all these type of catalyst and also their thorough characterization. So now I will show some of our examples where we are associated with industry, and we have been working on a reaction called amoxidation, where using ammonia and oxygen, you can convert this methyl group into nitrile in a single step. Actually, it is a multi-step reaction in the synthetic organic chemistry. But in industry, of course, there is the chlorination route. This is the route they follow, and then they remove the chlorine, so using a magnesium oxide. This is the practice now industry is following, and where it is a batch and you end up with the salts. So if you do this same reaction in the continuous vapor phase reaction, where this toluene and we can use ammonia gas and air instead of oxygen, we can use, and it is a highly exothermic reaction, and we can selectively get this one, and the byproduct is only water. So this is the one of the good example for the vapor phase continuous heterogeneous catalytic reaction. So we worked this orthochlorotoluene, which is a this product OCBN is used in the sartan family of drugs, is a starting material, and we did both ortho and parachloro for industry. And you can see we are continuously working, where we did more than 70 hours continuous operation with the stable selectivity and conversions, and for both. So we prepare the catalyst in different batches, and we will see we also have the reproducibility. So we did extensively on the synthesis of these aromatic nitriles. We also developed the catalyst for this type of nitrile compounds with the dichloro. This is orthoxylene, metaxylene, and this is cyanopyrazine, which is a precursor for the pyrazinamide, which is an anti-TB drug. So this is one of the example where industry, we worked with industry from the batch to continuous. We developed with the amoxidation process, and another one where when we are doing with amoxidation, one industry came to us because they are producing acid chlorides, and they are using aluminum chloride for the synthesis of these alkyl phenols. And what they are, can you replace aluminum chloride with a zeolite? Or even if you don't use acid chloride, if you use acid also, they are okay. And then we tried, but you cannot control the deactivation because of the HCl. So we generated the regenerability of the zeolite catalyst, but still that is not economically viable for them. Then we come up with an alternative approach. Instead of benzene, you can take, sorry for the mistake, it is a benzoic acid. If you take benzoic acid and this same acid, then you do the ketonization reaction, you will get the same product, and the byproducts are CO2 and water. So then once we told this alternative approach, then they are readily agreed, and we gave our initial report. Then they did their economic calculation. They said it is economically viable for them. So with this approach, you can it is a homogeneous and batch reaction, and where aluminum chloride handling is difficult, and you have to handle the byproduct HCl, and you uses the acid chloride. So when you adopt this one, is that a continuous process and heterogeneous, no acid chloride, and water and CO2 is the byproduct. So this is a very clean process compared to the present existing one. So then we did different molecules for them, and of course we initially developed a catalyst for this diethyl ketone, which is a solvent. You can propionic acid, you can so you can see we studied more than 80 hours with almost quantitative yields. So 100% 2 moles of propionic acid gives this diether. So in like that we did different molecules with this approach. Here the catalyst is simple oxide, mostly it is manganese oxide based catalyst. And we demonstrated to the industry this particular 2 molecules in higher scale where the catalyst is 100 gram, so that every this is 100 grams production per hour. Okay. So you can see here these 2 molecules with the same catalyst can do this 2 different reactions. That was the beauty of the catalyst what we developed in the bench scale and also demonstrated to them at I cannot say is a real pilot scale, but is a close to pilot scale. And with this approach we able to we solved the problem associated with the aluminum chloride. So this is the one example where we developed a heterogeneous catalyst required for the industry. So similarly, we also worked with other industry where they are still using aluminum chloride. They also came for the approached us for the development of a zeolite catalyst in the batch process. But still we tried batch process, we are not able to do. Then we went to continuous reaction vapor phase, this pichloroindanone. Of course, here also we are facing the deactivation, but we developed 12 cycles where you can regenerate and reuse, and this is the average activity we got. So wherever there is a opportunity where this heterogeneous catalysis will come to the rescue, where you can have a pollutant reagent or a catalyst, or it is in a homogeneous, you can convert into heterogeneous. If it is a batch, you can convert into a continuous process. That what we are trying to do in the fine chemical synthesis for the industry, particularly after post COVID era. A lot of industries are looking for the development of some of the starting materials because they are all dependent on China. So here some of our not exactly, we are not associated with industry, but for our academic interest, we are working on different catalytic systems in the batch process, and also then we are converting that. For example, this is a furfural where you use 20 bar hydrogen pressure to get with this cobalt based catalyst to selectively get this furfural alcohol, but you can does the same reaction in the continuous where you don't require any pressure. It is done at atmospheric pressure, and there the temperature is around 200 degrees centigrade. So like that you can convert the existing batch into continuous mode. And similarly, where this is another one we have been working on the reductive amination, where the aqueous ammonia and hydrogen is used in high pressure to get this amination product. And still now because we are working with an industry, so we convert that into continuous phase where you can use ammonia gas instead of aqueous ammonia, because handling of aqueous ammonia and then separation is then with this continuous approach where you can directly use ammonia gas at atmospheric pressure. This is the advantage of the one of the good example for the conversion of batch into continuous mode. And this is one interesting, recently we are also working with an industry where they came for the deuteration of benzene. Okay. So this is a very, because if you want to get almost 99% conversion, this you have to do repeated cycles, and where we used and around 35 bar and the reaction time is 20 hours. So to get 99% I need minimum of 5 to 6 batches, and the benzene handling and really is a very serious process. Then we tried, why can't we try with the continuous? And here the problem is you get the, for example, here I am using platinum carbon, commercial one, you have 50% moisture, and that moisture, it is a water that also troubles your deuteration. Okay. But when you have the continuous reaction where you do not need to take palladium carbon with moisture content, where you can have palladium and you can reduce in situ with hydrogen before starting, so that you do not expose and you can have a without water, and you can use, even handling is easy because you can take palladium not in the metallic state, palladium in hydride form you can take or oxide form, then you reduce in situ and do the reaction, and almost we got similar activity with the continuous. So, this is one we explored and we got reasonably good results when we convert the batch. This is instantaneous, of course still we used pressure, because here replacing of 6 hydrogens with deuterium is not that easy, but still continuous came to our rescue, particularly in this reaction. So, there another vapor phase oxidations where we designed a catalyst where we required a monomeric vanadium sites for this particular oxidation, where earlier this benzylamine oxidation is mostly reported in the liquid phase, but we did in the continuous and we published it in a green chemistry and developed a catalyst, oxidation catalyst on the polyoxometalates, and we can get the similar activity in the continuous mode. This is another oxidation example from batch to continuous. Similarly, we have been working on the biodiesel synthesis, and where the glycerol is the byproduct, and where we are looking for its conversion into useful chemicals. One is you can convert that into glycerol carbonate. Okay. So, this glycerol carbonate is reported with our catalyst. We also did a lot of work in the batch process, and where you use around 1.5 hour time at 90 degrees centigrade, you end up with around 60% yield. And then what we did is we converted into catalyst, because into continuous, but this is not the vapor phase, because we did at around 270, 290 degrees centigrade, that temperature glycerol will be in the liquid gas. So, still we can say it is a liquid gas and solid interface reaction, and it is a continuous, and we got reasonable good activity compared to the batch process. So, like that we converted the batch process into continuous mode. And another one is sorry, here I made mistake, I just copied. So, it is a 1,2-propanediol glycerol hydrogenolysis, where we use in the batch, it is well reported. We also studied where in the batch you will get a very good selectivity to 1,2-propanediol with reasonably around 40% conversion. But same catalytic systems, we of course cobalt, and we did also same catalyst, and where we used the continuous process and we got the good activity when you convert the batch into continuous mode. So, it maybe depends upon how you make the catalyst required for the heterogeneous catalyst, because in this case the surface phenomena will be different when compared with the batch mode reaction. Yeah, this is the another example with the same catalyst systems we did in the batch process, and also we did in the. So, of course, there is a bit decrease in the selectivity, because it is a two-step reaction where the acetal is the intermediate, then it undergoes further hydrogenation to put the 1,2-propanediol. But it is a continuous, so that is why the selectivity is required. But you see the time required for this reaction over this catalyst is around 8 hours. So, it is a continuous reaction. The temperature is more or less only 20 degrees variation. So, this is one of the good example where you can convert the batch into continuous mode. So, like that depending upon the requirement of the fine chemical synthesis with the industry, we mostly associated with the industry where we are also seeking for their required their problems where we can help with the development of this heterogeneous catalyst. So, like that we have been working in close association with the industries, particularly not many from Hyderabad, they are all from Dahej, Baroda, they are, because they are working mostly on the synthesis of the starting materials. So, now as a alternative, the biomass to the petroleum refinery, this is from the lignocellulose you can make a variety of products, either they are the platform chemicals or specialty chemicals or fuel additives. So, here lot of reactions are involved, and here the selectivity is the big question mark, maybe because it is hydrolysis, isomerization, dehydration, coupling reactions, caramelization, condensation, there are variety of that. So, there is a lot of scope to do, and most of the one uses the acid catalyst. So, here people are working to make a selective catalyst where you can do some of these reactions, particularly we are working in this direction from cellulose to all these DMF, EMF, FDCA. It is a basic work we are doing, but maybe in the future industry also requires to do some of these platform chemicals as a sustainable chemicals to the petroleum refinery. So, there is a lot of scope for the development of this heterogeneous catalyst for the in the continuous, maybe in certain cases, in this most of these cases we are working on the batch. Maybe next when you design a selective catalyst, you can go to, in certain cases you can go to continuous also. Of course, you may not do all continuous, or maybe if you can convert the homogeneous into heterogeneous, or heterogeneous batch to continuous, heterogeneous continuous, that may be advantageous for the industry in terms of the economic and environmental aspects. So, for that what we are trying at IICT to in the understanding of the catalyst and developing of the catalytic process required for the synthesis of fine chemicals. So, that is what I want to share with you some of our work what we are doing at IICT. So, heterogeneous catalysts are going to play an important role in coming days, and it is particularly the required thing is in the synthesis of fine chemicals and also key starting materials, and hope heterogeneous catalysis. Once you have larger scale, I think Professor Anil knows how to convert that into flow. So, for the development of the heterogeneous catalyst, you can first work at the fixed bed reaction. He also told that you have to work in the fixed bed, then come up to the flow system. So, there is a scope for both continuous and flow systems, particularly for the heterogeneous catalysis. Thank you for your kind attention.
I think we have got time for 2 questions.
I like that ketonization reaction. Yes. So, that's known earlier. What type of catalyst?
Is known, but not in the vapor phase conditions.
So, what type of catalyst and temperature?
There are these are mostly acid based catalysts used. In certain cases manganese based or works, and certain cases magnesium. There are 2 mechanisms exist in this one, where is bulk mechanism and surface mechanism. In the bulk mechanism, because it forms the carbonate and then decompose, because one CO2 has to eliminate from one acid. So, depending upon the, if it is a vapor phase, generally manganese, zirconia systems will work.
Okay, interesting. And temperature is very high there, 600?
There are 300 to okay. 400, yeah. Depending upon the reactants, because we are dealing with benzoic acid, so bit high temperature.
Yeah, my question is related to the shape of different supports. So, like you have many different support, So is there any rule of thumb which shape to be chosen, and like if you have data for one shape, is it transferable?
It depends upon the operating conditions, because when you are doing at high temperature, then and the flow of, because that all depends upon gas hourly space velocity. Because you have a high velocity, then your particle should withstand that pressure. Okay, and also there should not be any pressure loss. So depending upon that, there are some halo, and you cannot generalize. It depends upon the reaction and reaction conditions.
Thank you, Dr. Ling. Actually, it's been, I mean, OCBN, you are right.
Yeah.
It's music to the pharma ears.
Yeah.
I think Hyderabad should take more strong notice of this. I just had a general question about fixed bed catalysis. When you look into the example that Professor Anil also mentioned, the ketonization reaction. So when you have a catalytic system, but you look at different acids, do you see that in some cases there is a drop in the activity faster? Means there is initially very good yield, but there is a
Yes.
potential drop, assuming that as a function of time.
Yes.
And it happens from substrate to substrate, it changes. So that is the first question. The second thing is, how do you know that in a fixed bed system at some point of time you need to assess the catalytic deactivation and figure out a way to still be continuous by moving into a
Regeneration.
either regeneration or maybe bypassing it?
Yeah.
I think these are technically the challenges in manufacturing.
Yeah, actually in this there may be here, because the catalyst deactivation depends upon the raw material or the byproducts, or either there is a carbon formation. Main is carbon, or like in certain cases byproduct like HCl. In other indanone where we have the chlorine is there. So depending upon that the deactivation occurs. But because for example these catalysts will work for hours, and to estimate the real life we cannot run for so many hours, 500 hours. Then in that case what we will do is we will do high throughput experiments. So then so that we will see at what time. So if for example 10 grams of catalyst we are passing 20 ml of your reactant. So instead of 20 ml we pass 40 ml, 80 ml, and see the profile. Is there a deactivation? Like that we estimate. The high throughput experiments, then you can estimate the life of the catalyst.
I've got very quick question. In your OCBN synthesis, what do you mean by selectivity? Because if I understand the mechanism, you are oxidizing to make aldehyde, then imine followed by another round of oxidation. So, and your yield is in the order of 99.
The selectivity is 99, yield is around 75 to 80%.
Other way around.
Conversion, yeah.
So, selectivity with respect to what?
Selectivity with respect to product OCBN.
So, you will
there is a byproduct chance is either you may, here in this case we observed a less than 1% dechlorination product. So benzonitrile we got.
I did not.
And the other problem is if the hydrocarbon can undergo excess oxidation, you will get with COCO2. But we worked below 400 so that we avoided the COCO2 formation. So only in this case byproduct is the dechlorination, and dechlorination is occurring from the product, not from the reactant. That also we studied.
Other thing, do you have any plan to couple your parachlorotoluene and OCBN through Bitgard? Because that is another challenge.
That my organic colleague friend is doing. I think NCL also doing by flow chemistry, I heard. For OTBN, no, you are talking. Yeah. IIC, my organic colleagues are working. That is not through catalytic process.
So I spoke to, we will talk offline.
Yeah.
To internalize OCBN chemistry.
Sir, one of the slides you mentioned about this reductive amination. In that one of the undesired product is
Yeah. Yes, we are facing, we just started that into content, though that's why I didn't put the activity data. I put the activity data of only batch process, and continuous process we started, it is working, but I have not shown the data because of the, now we are fine tuning the catalyst. But we are doing that. Yeah, is there, yeah. So we want to avoid the aqueous ammonia.
Let's give him a round of applause for very interesting talk.
Thank you so much, sir. May I please request Dr. Rakeshwar to hand over a mentor to Dr. Lingaya? Thank you, sir. I also request Dr. Srinivas to hand over the mentor to Dr. Rakeshwar.
Dr. Rakeshwar still has to chair a couple of lectures. Favor from him despite this. I know, I will get
Thank you, sir. So we'll be now having a lunch break. We'll assemble here back at 1:50. Thank you so much.
next time if I come to Germany, I'll let you know.
Yes, please, you should. This is
What and give it back to me.
however, please give me 6 months. We're already voting till January Europe's Christmas 2020 program.
Yes, everybody likes to have their metro is there, people like their So if metro was not there, we would have been a much bigger traffic. Come this
of the day. I request Dr. Rakeshwar to please come and head this session. Thank you.
So welcome back. It's going to be post-lunch session, and the speaker is Professor Ashwini Nagia. I think he doesn't need introduction. Just to brief about his current position, he's a dean of the School of Chemistry at University of Hyderabad. He held various important positions in past, like he was director of NCL Pune and all. So with this brief introduction, sir, stage is yours.
Yeah, thank you. It's there, I have one. Okay, thank you. Thank you, Dr. Rakeshwar, for the introduction, and to the audience for coming back after the lunch break. I think this is one of the most difficult slots to speak in. The next one being the last one for a one-day meeting, when everybody tells you, look, my flight is on time and I have to rush, but I'll certainly catch you next time. So my job is to keep you awake when I think sugar levels are one of the highest in the body after a sumptuous lunch and people want to relax. But I want to assure you, after the wonderful talks we had this morning from Professor Jerome, Professor Anil Kumar, Dr. Lingaya, there is very little left. They have taken all the, the early pickings, the low-hanging fruits, the popular and the favorite buzzwords. The only thing I want to add here is that flow chemistry, as very persuasively Anil has campaigned, it's a new subject, so one has to learn a new language, a new grammar, and also stretch the boundaries of one's learning from what one already knows. And of course, the maximum overlap it has, and also the interest is for the synthetic chemist. And let me add here, I myself was trained as a synthetic chemist, but now for more than 3 decades I have worked in a different area. So it's possible to learn a new area. That's the first thing I want to assure you. I myself am a newcomer to flow chemistry. I learnt it about 5 years ago, and I was introduced to this subject when I moved to NCL. I found it very fascinating, and just like what Anil said, I watched videos, I attended lectures, and I think if you have good friends and you are polite to them, even though you don't work in the area, they'll call you, and so you can learn a few things. And that's how I learned the subject. I didn't follow any formal book. After I came back to Hyderabad University, I again had a very tough time, but I succeeded in convincing my colleagues in the chemistry department that's an important area. And I was able to convince them, and so we have floated a flow chemistry course as an elective, but nothing to do with me. I think it's very popular. We have had 70 plus registrations in the last 3 years. That is 22, 23 and now 24 we just started a month ago in January first week. So this is my contribution to the area. I don't actively do research in the area. So what I want to do is revisit some of the topics that we and the nomenclature we heard in the morning, transition states, reactive intermediates, kinetic versus thermodynamic products, mixing, exothermicity, how to take care of heat, solvent, sustainability, green chemistry, how to minimize waste. These all overlap with the essentials of flow chemistry, and that is one of the reasons why flow chemistry has taken on, notably I will say in the last decade. Although if one really goes back, it's a subject I think today of about 20 years young, or not so young as you may call it. So these are some of the advantages we have heard, we have seen them. It minimizes solvents, small footprint, scale up is always there will be surprises, but much less so. I think a log scale less than batch chemistry will be scale up in the flow. It's particularly suited to fine chemicals, perfumery chemicals, agrochemicals, pharmaceuticals, because these are all high value items. You want to manufacture them, but also do them economically, and also competition is getting very stiff. And also now post COVID there is also this China plus one factor. People would like to distribute their manufacturing in multiple locations, and as we heard in the morning, this is doable with mini platforms. The most important is you integrate synthesis with inline and online analysis. So it gives you a picture just like Google Maps of what's happening to your reaction as it's happening. So you can take mid-course correction. You don't have to go to the end of a 4-step synthesis, realize you have an impurity and then go back 5 steps. You spot an impurity, you can stop the reaction and say, okay, maybe this particular material is not so good, but the next one that moves behind it will be of good quality. So you can do it much faster, as we heard in the morning. Essentially flow chemistry is nothing but how human body works. Inside our body we have many biochemical reactions, but it's always in a flow. Of course there are headwinds, and I think the biggest headwind is the mental block which many chemists have, but despite that I think it's shown a dramatic improvement in the last 5-6 years that I have been associated with it. One does need to convince, but I think that convincing is getting easier by the day. One of the biggest advantages of flow chemistry is that it aligns with green chemistry and sustainable development goals. Again, it's a buzzword, not to be overused or misused, but I think sustainability, there is only one earth as we know, is important, and out of the 17 flow chemistry, both the chemistry part and the chemical engineering part, you see several tick marks here. This is just a head-to-head comparison of batch versus flow. You can find it in many textbooks, many reviews. Today I will say the subject is quite mature, and if you want to read about it at the beginners level, at the intermediate level, and at the specialist level, you can find a book. There are journals dedicated to flow chemistry. It's just repeating what I just said, that these are some of the good things about it. There are some headwinds, but I think solid handling was an issue some time back, but with time and with technology things are getting better and better. For pharma, the most important thing is FDA. It's not optional today. I think FDA almost requires and mandates that you have a dossier in flow when you submit your, correct me if I am wrong, almost it mandates, and so do other regulators, because you get much higher reliability, much higher reproducibility, much less of the impurities, and if you get an impurity, it's usually below the limit that is normally allowed, which is less than 0.1 or 0.2%, whereas in a batch you may see like 2%, 5% impurities. And we heard some of the reasons, and I will try to show again, re-emphasize in a slightly different way why we see less of impurities and much more of reproducibility and repeatability when it comes to flow chemistry. So this is our RB flask. Now for more than 100 years batch chemists have been using it, and these are some of the definitions. Some in the room may slightly have different versions of it, but essentially batch is a series of operations carried out one step at a time. You isolate the product, go to the next one, load the material in the next flask, and so on, and each is an identifiable separate step. Flow is, on the other hand, a continuous series of operations where you really cannot demarcate that step 1 ends and step 2 begins. It kind of, as the name suggests, runs in the flow. The isolated yield in batch becomes actually a combination of the flow rate and the residence time, and we saw that in the morning also. Process intensification is a term which sits between these two disciplines of flow chemistry and batch chemistry, which is how to improve the rate of mixing, and this is very important, and I will also try to emphasize the same. Reduce the reaction time, but keeping it in a safe zone. That is important, because you do not want to have situations where the reaction goes out of hand. So this is our round bottom flask, which all chemists have been using and still use. Typically the flask should be half full, and this table shows the volume of the liquid, which is what is shown here, about half the flask size. So this would be a 10 ml flask with 5 ml of liquid, 25 ml, 100 ml, 500 ml, 1 liter and then 100 liter. And as you can see, the radius obviously will increase, you are going to a larger and larger sphere, and so will the area. By area I mean the surface area, and by volume I mean half the volume of the flask or the volume of the liquid. And as we saw in the morning that the two do not increase or vary in the same proportion. The surface area is much larger when you have a small flask. The surface area is much less relative to the volume as you increase the volume, and therein lies the biggest devil in the round bottom flask. We are comfortable with it, but what we did not realize is that because of its geometry, scale up is an inherent limitation when you go from 5 ml to 50 ml to half a liter and then to 50 liters and then 500 liters, or a huge reactor which could be a cylindrical in shape, but essentially will carry the same geometric limitation. So this is the surface area to volume which you can calculate in an Excel sheet, and as you can see, for a 5 ml flask it is 1, and for a 100 liter round bottom flask it would become 4% of that. So if this is in centimeters, if you calculate it in meters, this would have a value of 100 and this will have a value of 4. So essentially, as you scale up from lab to pilot plant, your surface area to volume ratio gets worse, and you can do this calculation on your own or use any simple calculation. Now let us come back to 1 ml. 1 ml is kind of the smallest, I think, batch reaction, almost like a small test tube you would do. Your radius would be about 0.8 of a centimeter, and your surface area to volume would be typically, let us say, 2. And why did I choose 1 ml? Because 1 ml is the beginning of, let us say, going from batch to flow. And I think this was mentioned by Anil also. Imagine a 1 kilogram reaction. In batch scale, a 1 kilogram probably would be run on anything like a 50 liter flask. But when you run it in flow, the same 1 kilogram reaction can be viewed as, can be treated as 1,000 1 gram reactions. So essentially, you are doing it in a 1 ml flask, but you are producing the quantity of 100 liter. But you are not doing 100 liters at a time. You are doing only 1 ml at a time, but 1,000 times, and obviously you get 1 liter. So from here, the best you can get in an RB flask, which is about the smallest size, is a surface area to volume ratio of, let us say, 2. Now let us keep the same volume and go from the traditional thinking, which is in the batch mode, to now flow chemistry, which is you stretch that 1 ml into a 100 meter long micro tube, and that 100 meter long micro tube will have a side of 100 micron. Again, you can do the simple maths and you will get that the volume of this micro tube and the volume of this cube are both 1 ml, and in the last slide we saw we get a surface area to volume ratio of 2. If it is a cube, and the reason why I have kept it as a cube is because if the cube was like a flow reactor of 1 centimeter side, it would be first fully filled. So the 1 ml will apply, not the 2 ml. Secondly, if this was a cube and it had 4 sides, you get a wall area of 4 times, which is 4. 4 is okay, not that great, double that of 2. But now you see this, when you stretch it as a 100 micron square tube with 100 meter length containing the same 1 ml, now look at your surface area, it has become 400. And again, I am just stating a number, you can go to the books and find it. Anything greater than 80, 90, 100 surface area to volume, you are good. You will get excellent mixing, you will get excellent heat dissipation. For most reactions, anything more than 100 is like, you can be in the safe zone, you can expect fast mixing, you can expect the exothermicity to be taken care of in terms of heat dissipation, and several of the problems that you face in the batch mode, you will kind of overcome them when it's. So essentially, what are the problems you see? Temperature is uniform in a micro tube. So when you have this 100 meter long micro tube of 100 micron on each side, you get a uniform temperature, you get fast heat exchange. So whatever temperature you think you should have, you will have. And I think this again very nicely Anil had pointed out. You may think the measurable temperature is 38 degrees because that's what your thermometer is showing. But because of exothermicity in the reaction, the molecular, the micro temperature at the molecular level may be anywhere between 30 degrees to 45 degrees to even 50 degrees, depending on what zone of the reaction you are looking at. So you get uniform reaction conditions, and that uniform reaction conditions is the reason why you see better repeatability, better reproducibility when you are working in the flow mode. Most important from a chemist viewpoint, again we heard this in the morning, kinetic versus thermodynamic products. Most of the times, not always, but I think most of the times chemists are interested in the kinetic product. Sometimes they also like, I think we saw one case where the thermodynamic product was the desired one. Getting the thermodynamic product is not so difficult because it's finally the more stable one, but usually chemists want the metastable form or the kinetic form, that is the one that forms early. And because it forms early, as the reaction proceeds, more and more of it is in the reaction flask, your RB flask, sitting around to react with whatever is your reactive species, and I think we saw several examples in the morning. So you will obviously get the second addition, the third addition and so on, which flow is able to solve for you. So this is a graph which shows the channel diameter, which is on the x-axis is 1 centimeter, and this shows the surface area to volume, and you can see you get 100 at about less than 1 mm, roughly about 600 micron. So if you have a 600 micron channel, the channel can be a square, but typically, although I showed the calculation with a square channel, but normally you have a cylindrical channel, the maths doesn't change that much. So with about 800 to 700 micron diameter, you can safely assume that you will get a surface area to volume ratio of about 100 or higher. Of course, you can go to lower and lower diameters, but I will tell you in a minute. Nothing in chemistry is geometric. You cannot go on reducing any parameter because it will have a counter effect. So typically 100 to about 50 micron is the range in which we like to operate, because the liquid has to flow. It cannot be a very, very thin microtube. Of course, there are also engineering issues. So when you have a good surface area to volume, you solve many of these issues which we have heard in the morning session. In several of the lectures we face in the batch reaction. Heat exchange is efficient, and therefore you can carry out the same reaction at a higher temperature. As we heard in the morning, why do we go to minus 78? I mean, I remember as a synthetic chemist when I was doing my PhD, 830 on the basement of most labs is the dry ice maker or the dry ice chest. There would be line of 20 people waiting to fill their dry ice boxes, because everybody wants to start their reaction at minus 78, not because the reaction needs minus 78, but the heat dissipation needs minus 78. And so you slow down the reaction, and as he said, we would let it run for 8 hours, 6 hours at minus 78. So you control the reactivity to the point where you get selectivity. You are not controlling reactivity, you are only controlling the temperature. You can get very good reactivity even at 0 degrees, and that's what flow gives you. So this is your sort of your magic region, 50 to about 150, 150 to 200 surface area to volume, and typically less than 1 mm, but probably no more than 50 to 60 micron is good enough in most cases. I mean, there may be other opinions as he. So we saw a part of this diagram in the morning also. Any reaction will have can lead to two products. There is a lower activation barrier G1, which leads to product P1, and then there is of course a higher activation barrier G2, which leads to product P2. And other than, I think, polymorphs in pharmaceuticals, where the chemists or the pharmaceutical scientists wants the thermodynamic polymorph, in most organic reactions that I know, whether it is enolates, whether it is Diels-Alder reaction, whether it is alkylation, whether it is acylation, whether it is Friedel-Crafts reaction, or even oxidations, you want to oxidize an alcohol to an aldehyde, but you don't want the aldehyde to go to the acid. That's also like a kinetic, you are stopping in the middle. You usually want P1, very rarely you want P2. Now what happens in a batch mode? Why is this curve so huge in the batch mode but so narrow in the flow mode? The reason for that is shown below. We are not reacting one molecule, we are reacting a Boltzmann ensemble of molecules, and this is your Boltzmann distribution because you have an Avogadro number of molecules. When the reaction happens, A and B mix, you may be mixing it at minus, let us say 30 degrees, but at the spot where A and B mix, the temperature may suddenly rise from minus 30 to minus 20 or may even reach 0 if the reaction is very exothermic. So there are some molecules which see or which experience a temperature of minus 20 degrees or 0 degrees, while your flask thermometer still shows minus 20 degrees or minus 30 degrees. And as you change the temperature, we know this Boltzmann distribution changes. And therefore, when you are doing in the batch mode, your energy range is much wider. Your energy range is wider because your temperature control is not there. You are setting it at minus 40 with some kind of cooling or a minus 78, but every molecule does not see minus 40 or minus 80. There are molecules which even see 20 degree, 30 degree increase in temperature, their Boltzmann distribution changes, this energy graph becomes bigger. In flow, you are able to maintain, because of the high surface area to volume, minus 30 means minus 30. 99% of the molecules will see minus 30 degrees only, unlike batch where probably 10% will see the temperature you have set and 90% will be randomly seeing at some point of time a higher temperature, and therefore their reactivity will be different. So therefore in flow you have a much calibrated control on the temperature, much calibrated control on the energy of the molecules, and therefore a calibration on the product you get, which is the kinetic product and not the thermodynamic product. So a minus 78 reaction does not need to be run at minus 78 just to dissipate the heat. It can be run probably at minus 30, and this is true for many Grignard reactions, ozonation reactions, alkyl lithiums, which typically you go all the way down, you can run it at somewhere between 0 and minus 80. Another paradigm which we were always taught as students, that selectivity and reactivity is like a seesaw. If reactivity is high, selectivity is low. I mean, I have myself taught that in all the physical chemistry classes. If selectivity is low, reactivity is great, but you want selectivity, so you go to low temperature. Flow gives you both, as they say, BO, what is it? BO-BW, best of both worlds. I think all of you know what that means. I learnt it from one of you only, those sitting in the row 3 and beyond. So this gives you BO-BW, best of both worlds. You can run your ozonation and your alkyl lithiums at minus 40. You can run your Grignards sometimes at 0 to 5 degrees, which typically require minus 30, and I mean those sitting in the front row will tell you the amount of cost savings every 10 degrees not going down in low temperature gives you is enormous. So that is what it gives you, better control of the conditions, better control of temperature, and therefore you can get both selectivity and reactivity at the same time, and when you get fast reactivity, your reaction time becomes less. You can do it in a few seconds instead of 6 hours at minus 78. This is a few graphs to show you. I think people need convincing. This is an acid based titration. I think what you just said is very true. It probably femtosecond, definitely 10 raised to minus 6 to 10 raised to minus 8 nanoseconds. You are mixing hydrochloric acid and sodium hydroxide. This is when you are doing in a normal mixer. You see the concentration hotspots. This is all blue, which is sodium hydroxide. This is all red, which is you see a very few green spots. Okay, and this is when you do it in flow. You have your blue coming. You put in HCl, and you see in less than half a centimeter, you have reached a uniform concentration or a uniform distribution of the mixing of the two reactants to give you the neutralized product of the titration. So here even after several minutes you will see hotspots of high concentration and low concentration of reagents, which will, of course, in sodium hydroxide plus HCl there is no side reaction, but imagine if you are having multiple reactants, they will give you multiple products because of the hotspots. This is the temperature control. Both the channels, although they are of different width, I am emphasizing, are of the same diameter, that is 70 micron. This is the temperature control when HCl and sodium hydroxide are mixed in a 70 micron channel, and this is at room temperature 293 Kelvin, and you can see it barely goes to 296, maybe 297 or 2. So just about 2 degrees increase in temperature happens when they mix in a micro channel. Sodium hydroxide plus hydrochloric acid, I think all of us in our naivety have tried to add the two, sometimes out of fun, but it is really exothermic. That exothermic reaction is causing only a 2 degree increase in temperature. That is the power of flow, that is the power of a micro channel. Okay. Now just one or two examples to quickly show you how you can reduce the number of steps. Fluorination, I think there are many hazardous reagents, diazomethane, isocyanates, ozone, hydrogen, fluorine, so many we heard in the morning, where you want to handle them safely, and fluorine is one of the most difficult ones. This not only reduces the number of steps for a pharmaceutical KSM, I think this is from the group of Graham Sanford at Durham. In one step from cytosine you can make fluorocytosine, which in several grams per hour. Now it is not that flow does not require optimization, you get a bit of this byproduct 3 because of the dual addition of the fluorine to the product, but you can, as you can see, you can almost minimize it to greater than 99% conversion, greater than 95% of the product and 83% yield, which would be several steps if you did it in the batch mode. Now there are 2 kinds of configurations, you can pick one or the other when you have a gas liquid reaction, diazomethane, hydrogen, ozone, fluorine. Either you can have gas inside, liquid outside, or the other way around. The surface area which is exposed changes, and so depends on what you want, what is the hazardous nature of the gas, you can have it inside or outside, and one can kind of work with those things. But essentially these are the 2 main geometries available for a gas liquid exchange reaction, and this is typically a semi permeable kind of membrane which allows exchange of the reactants, the gas and the liquid. The next reaction is butyl lithium, what I have been just saying all along, minus 78 is the standard temperature, but you do not have to run it at minus 78 in flow. This is from Pfizer, where you take aldehyde, is a very reactive species, make the lithiated species, exchange with zinc, add to this aldehyde, and you get this chiral homopropagyl beta amino alcohol in high yield, high throughput and substantial cost savings. 0 degrees. I do not think in any synthesis lab an alkyl lithium has ever been done at 0 degrees. Imagine, I mean Dr. Rakeshwar will say 0 degrees versus minus 78. You know, you will get good increments if you made that process change in the industrial R&D. The last I will run through quickly. This is again an example where you get a product of mono addition, but the mono addition product reacts again with the reactive species and gives the bis addition, and as I said, most chemists are usually interested in the first product. If you want the second, then there is not that much of a really a DOE or a design of experiment required. The challenge here is that while in most Friedel-Crafts acylation the mono product is deactivated and therefore reacts slower than the starting material, if the alkylation is having with a slightly electron donating or electron neutral species, then the second reaction is faster than the first one. So as you build up the starting material, the second product also starts building up, and so you get a lot of the bis product. Of course, there is an ortho-para ratio. The ortho-para ratio is typically 30-70 or so, but there are ways to increase the para part. Here our main focus is how to minimize the bis product, where the second reaction is faster than the first reaction for the same diazo species, which is this sulfinate diazo species. So, since mono is slower than bis, the contact of mono gives diffusion. So, what you want is that the diffusion and mixing must be comparable to your reaction rate. It can be a little faster or it can be about that, but if diffusion and mixing is very slow, which is what happens in a batch reactor, you will get more and more of the bis addition because your mono product sits in the flask. I think we have already covered this point. So, you essentially the idea is if you can increase the flow rate, so that diffusion and mixing and reaction rate are roughly matched, then you will get maximum of the mono and minimum of the bis. So, you can vary the micro channel diameter, tube length, residence time, flow rate. I think most chemists know this. It is just that they are optimizing a different set of parameters when they work with the RB flask. This is another set of parameters. I will just show the results. So, now there are different kinds of channels, as I said, new subject, you get new hardware also, just like your iPhone, new models are coming out. You can of course pass them through a micro channel, but to improve efficiency of mixing, you can split those micro channels into by 3, by 4, so that they become even thinner channel and then recombine them. So, your mixing efficiency improves as a function of n square. So, you can make 1 into 3 and then 3 back into 1, so that the mixing is more efficient. Okay. So, this is the T mixer, 1.25 mm diameter, T mixer meaning just a simple T, 0.5 less diameter, caterpillar mixer, which is kind of allows you to control different stoichiometries and flow rate, and a slit micro mixer of the type. You can see at 1 ml per minute, this shows the amount of the undesired bis product. If you did it in batch, you get about 50%, and that is a separate result. But if you did a 1.25 mm, 1 mm remember I showed you is about the limit of a micro channel. You get 50% of the bis. As you increase the flow rate as expected, you get less and less of the bis product or the undesired product. This is the undesired product. You go to lower diameter, you start getting less even at slow flow rates. You go to the caterpillar mixer, it even comes down. You go to the slit micro mixer at 12 ml per minute, you are having less than 1% of the undesired product. Now, somebody will ask, why don't we just keep increasing the flow rate? But we heard in the morning, as you scale the size, you can't have very high flow rate. You will get vertex, you will get turbulence, all those things are a separate subject. Then chemical engineering starts interfacing with flow chemistry. So, when you increase the flow rate beyond a point, you start getting turbulence. Turbulence is not that great because again it gives you something which is undesirable. So, you can increase flow rate, but only up to a point. I think 12 to 20 is a good flow rate. After that, you need pumps, you need many other things, hardware. So, you would like to achieve the mixing at a efficiency at a flow rate which is within your range, and that is where the diameter of the channel, these different kind of micro mixers, all that hardware sort of comes in. So, essentially you have very good control on the reaction, and you can get almost completely mono adduct with almost negligible amount of the bis adduct using flow chemistry, but not in the batch mode. And last but not the least, I think all the toys you need for flow chemistry, they were not available in India about 5-7 years ago, but today just about anything you need. If you have the money, buy the imported one. If you do not have the money, you can also buy the domestic look-alike clones. They are reasonably good. We ourselves have set up a lab. This is a very good review which appeared, there are many reviews, but this one appeared recently, and it is specifically for the, sorry, just to make sure you are awake, read it like this, it is specifically for the synthetic organic chemist. It says in the title, it is written by a synthetic chemist who has moved to flow. Last but not the least, several of my friends have always kind of guided me and told me things which are happening in this new area. I have learned from them. So, many of them are in this room today. Thank you very much. The Institute of Eminence at our university funded a small teaching lab which we are using for the students, and some of the slides were taken just directly from the lecture notes of Professor Oliver Capet, who gave a wonderful, of course those days it was online because of the COVID. So, I was able to attend, otherwise my scientific update normally you have to go to the UK and attend, but one of the fringe benefits of COVID was that they allowed online registration, and I attended his course, and so I took it from his lecture notes. Thank you very much. I think I am good. with the time. Thank you.
Might take 2 to 3 questions.
Basically, Professor Nange, I mean, trying to bring in your deep expertise on polymorphism and
I'm
solution.
learning. I'm no expert in
the
this
flow.
area.
No, but what is your just opinion on flow chemistry being the go-to approach for getting crystalline forms?
Oh yeah. People have used it. I didn't
I know that
cover
particle
those
size and other
examples.
things are being controlled.
But you know, alizarin hemifumarate is one of the first ones which went from starting material to the salt. The MIT Novartis example, I didn't show it because I thought many would have seen it and there's only so much time. There are several flow processes now, I think, which have been published, which have also been reviewed, where mechanochemistry and flow chemistry are coming together, particularly for crystallization, where one can do the twin screw grinding, the kind we saw in your lab upstairs, followed by mixing and then getting the formulation directly in a single
actually,
step.
That leads to my actual question is, what on the co-crystal, which are again very intricately bound hydrogen bonding structures, will flow be helpful or will it be harmful in the sense, because I'm not talking about the mechanochemistry or a ball mill equivalent but using a solution-based co-crystal approach. Is it worth trying, or you think we might actually?
Why do you think it would be harmful?
In the sense that we have to slowly allow the interactions to happen, and it takes time.
But
it's not usually
in
a very
our
fast
own
process.
experience, we use mechanical grinding often with
Yes,
coke.
I'm referring more to the solution based, not the mechanical or the ball mill equivalent.
See, solution based, not part of this talk, but generally solution based techniques are not the best ones for making co-crystals, because in co-crystal you are trying to bring two different molecules, two different chemical species in the same crystal lattice, whereas crystallization is inherently a purification method, and therefore solution crystallization is probably the last of the methods, because your solubility has to match, your supersaturation has to match for the two disparate components, your API and your salt former. So normally one actually doesn't use solution crystallization unless nothing else is working. Normally one would use mechanochemistry, which takes a few minutes, and it's very easily adaptable for the flow operation which we saw in your lab upstairs just before lunch.
Maybe it's a comment on the very good questions from Dr. Srinivas. What about Ostwald-Ripening? Because actually when you want to induce crystallization faster, you grind. This is totally counterintuitive for students, especially in the field of crystallization, so Segal enantiomers. You tell students, no, spin as fast as you want, because every time you make a crystals by grinding the crystals to macrocrystals, you speed up actually even the formation of the right crystals. So naively, I would expect that mechanochemistry would speed up the Ostwald-Ripening. Am I wrong?
Absolutely right. In fact, we often first make the nuclei, the seed nuclei, by grinding or micro grinding, and then use them for crystallization to get single crystals if we want the X-ray crystal structure. So yes, the A plus B floating in solution, entropy is too much to come there together unless it's very strong ionic bonding. So one way is to bring them together physically as a nucleus, and that nucleus then becomes, as you rightly said, the seed for the growth and Ostwald ripening. Absolutely. Yeah.
Do you have any more questions? I don't think so. So give him a round of applause for excellent talk.
Thank you.
Okay. So I'm repeating again. So the next talk is going to be delivered by Dr. Srividya Ramakrishnan, and she is a global head of CDMO Origin Pharmaceutical Services. And before that, she worked in IPDO, which is part of R&D center of Dr. Reddy's. And before joining Dr. Reddy's, she worked for BMS, before that Unilever, and did PhD from Princeton University and Masters from IIT Madras. So with this brief introduction, I would invite Srividya to talk about integrating downstream operations for continuous API manufacturing.
Screen share. This plugged in, right?
Yeah.
Yeah.
Hello.
Okay. The pointer. No, to change the size of the slide screen. Oh, it's the, okay, great. It's okay. Yeah, hi, am I audible? Yeah. Okay, great. Yeah, thank you. Thanks, Dr. Rakesh, for the kind introduction. And thank you to Dr. Srinivas for inviting me to be here. Very happy to be here with all of you. And, I think you also very nicely between you and Professor Nangia set the context for my talk. So I think half my work is done now and I can relax. So, so coming to this topic, I'm going to shift a little bit beyond what we have been discussing since morning, which has been a lot about reactions. So being a chemical engineer, well, I also worked on reactions, but being a chemical engineer, I'm happy to also talk about, what we do beyond reactions, right? And why should we look at further downstream operations, such as crystallization and so on. So first of all, I want to acknowledge, this is a lot of work that has happened over the last several years. And Jagan, who's here, has been, a very integral part of it. And we have developed all the way from reactions to downstream operations. And I want to acknowledge the entire team who have contributed to this, while I'm just the face of it here today. So this will kind of be the outline of my talk. Why do we want to integrate, downstream operations as well? What is the motivation for doing so? And how do we go about doing it? Well, we heard a lot about reactions. If I have to, look at a crystallization process, how do I really develop a continuous crystallization process? And then take it further into filtration and drying. And to really combine all of these, what are the various aspects that you have to think about? So this is a little old data, it's got to be refreshed, but this was a nice article we found a few years back, which kind of summarized, the number of publications in looking at various unit operations in continuous. So of course, there's a bunch of stuff on reactions, but crystallization, and filtration was very less, and formulation has also picked up quite a bit. And we also know there are commercial products out there with commercial manufacturing for the drug product. Right, but if you look at the crystallization filtration, it's an area that's not been explored too much, though there have been a few studies on this. So if you look at articles, who's really talked about continuous crystallization and why are they doing it? The motivation changes, and there are many publications, notably like I think you mentioned, for Alice Kiran. There was some work that was done at MIT where they looked at, again, integrating the process all the way through from reactions up to the, in fact, up to the drug product, if I'm not mistaken. So they had done a bunch of work on integrating this. And there's also been work at Purdue and Eli Lilly. In fact, they both collaborated. And Eli Lilly's published quite a bit for the last several years on continuous crystallization. They get better impurity control, especially for impurity rejection, particle size control, and so on. And there have also been, I think, a lot of motivation, I'd say mainly around particle size control as well as integration with the reactions. And why would you actually want to integrate with reactions? Well, of course, a reaction by itself, can be much more effective, in flow, as we've heard, right? But you also have the advantage that if you have a high volume product, you don't then need to batch it, right? Because then you're always going to just do your reaction in flow, and the rest of it would be in traditional batch reactors, which kind of also defeats the purpose, especially for, I would say, high volume products, because you can get a much lower footprint if you integrate it all the way through, right? Otherwise, you will have, you know, a lot of volume being generated in your flow reactor, but then you will have huge, you know, crystallizers that are sitting downstream occupying a lot of space. And just as the example that was shown earlier this morning where, you know, the MIPROVA replaced, you know, a huge number of large scale reactors, the same is true for crystallization as well. So, and when you integrate all of these end to end, the other major advantage is you get absolute consistency all the way through, and especially if you're thinking about API, all the way through to the API. And that was really our motivation when we got into this. It was not a particularly challenging reaction, but it is a high volume product for Dr. Reddy's, for which we wanted, you know, absolute consistency and robustness going all the way through to the API. And that's why we designed a process that consisted of 3 reactions, well, 2 and then the salt exchange, a byproduct filtration just to remove some salts and junk, and then getting into, you know, crystallization filtration. There's a delumping I'll touch briefly upon, and drying. And while I think reactions are well spoken of and I'll talk about this, I just want to take a minute to also say that this byproduct filtration was in fact one of our very unexpected challenges, which we never focused on during the entire development, right? We thought, oh, reactions are done, crystallization is done, and everything is wonderful. And then we realized what appears so simple in a batch process where you prepare a high flow bed and you filter it. How do you actually do it in a continuous setup, right? So I'm not going to talk on the first 3 or first 4, but I'm going to just touch on this little bit briefly right now before I proceed to the rest of it. So in fact, we got these automated, you know, byproduct filters where you have plates and the whole, you know, the high flow bed can be prepared on these plates. We got 2 of them. So we pump so you have a continuous stream of the solution containing, so by the end of the salt exchange, it's a supersaturated solution of the API, right, that's coming through. It has the right purity, you just need to wash off these salts, right, or filter these byproducts, and so you pass it through this automated, you know, filtration setup with a high flow bed prepared. It keeps going through that, have a second one and a way to alternate between the 2. So once you see a pressure rise in the first one, automatically switch to the second and then come back to the first. So of all the setup that looked complicated, this looked really complicated with a lot of valves. So the reason I'm just bringing this up is sometimes you can be surprised by very apparently simple operations in batch, which actually pose an unexpected challenge when you want to do it in flow, right? But if you can tackle these, then you know we can really progress. So I'm going to focus on crystallization, and of course, you know, with Professor Nagia here is really the expert on all the solid forms. Any API, you know that you've got to have solid form control, right? Whether it's the thermodynamically stable form or not, you really need to demonstrate that control for solid forms. And in pretty much every API, you also have to demonstrate control on the particle size. In this particular case, we didn't care about control on particle size for the final product because there's anyway a micronization operation at the end. However, we did care about it because it's linked to the next operation of filtration, and I'll talk more about that later. So this API had basically multiple forms, of which this form 1, which is a trihydrate, is the desired one, and there's also kind of a semi-amorphous form as well as a dihydrate, which commonly, you know, show up during a typical crystallization process. And when we are, I'll just step back. So one of the keys that really helped us, key things that helped us to do all this was when you talk about, you know, intensification and simplification, it's also finding a solvent system that is suitable for this entire, you know, set of unit operations. So we had essentially the same solvent system for the reactions and then into the crystallization. So we wanted to eliminate solvent swaps and distillations, and if you can identify such a system, then it, you know, greatly simplifies the whole process. So we had a mixture of IPA and water for the reactions, and when we get into crystallization, this is the solubility as a function of the percentage of water. We are actually right around here where the solubility is maximum. So it shows a slightly synergistic solubility, where as you add water to IPA, the solubility of the API increases, and as you add more water, the solubility drops, right? And these are just at different temperatures. So we are coming in here at 65 degrees at the end of reactions, right? 65 degrees in this ratio, and we basically want to maximize the yield. So, we are dropping the temperature and we are adding more water. So, we come in from this gray triangle here down to this blue diamond at 25 degrees as we add water in there, right. And we optimize the amount of water to maximize the yield, but also while being cognizant of the effect that it might have on impurities. So, there is a bit of trade off, and those are the two that we optimize. So, this is all done in batch, very simple, very straightforward, right, very classic crystallization process development. And this was the batch crystallization process that is actually that we helped develop, and it's in our commercial plant, which is basically you have the solution of the API in a mixture of IPA water at 65 degrees, and it's added into water containing the seeds of form 1, which is the desired form. And the reason it's this reverse anti-solvent, what we call this is a reverse anti-solvent addition, where the API solution is added into the anti-solvent, and the reason for doing this is for the polymorph control. So, if you don't do it this way, then we get the other forms, form 5 or form 4 that show up. So, to get form 1 consistently, you already have the anti-solvent with a seed bed into which the API solution is added, and then you cool it down gradually from 65 to 45 and 25 and go further. So, again in the batch process, cooling is a very simple operation. You just say cool it from 65 to 25 over 3 hours or 4 hours and your job is done. So, very simple, but again doing this in flow, in continuous, not so simple, right, and I will talk about this. So, we were happy, we had a very robust batch process. We said, okay, if I were to do this in continuous, looks straightforward and simple, right. So, we just have to add our API solution and our anti-solvent together coming in as 2 streams, they are going to mix, and I am going to get form 1, right. So, we thought we will be done with this in a week, yeah, and we went very optimistically, and we saw all the Eli Lilly papers where they done these CSTRs in series, right. We said, okay, we have 3 CSTRs, just regular reactors in the lab, 65 degrees, the 2 solutions come in, they mix, cool it to 45, cool it to 25, do it in 3 steps because you can't do a gradual cooling, and out comes the product. Well, out came the product, except it was a mixture of form 1 and form 5. So, we could not get pure form 1, right, or we got a mixture of these 2 forms, and we could actually see that over a period of time it became more and more amorphous in nature. So, this was clearly not working out, and we started breaking our heads about what's happening. We said, well, there's a huge jump from 65 to 45 in solubility. So, maybe there's too much supersaturation, it's a shock, with all our knowledge of batch crystallization. We said, let's take one more step in between, we'll do 65, 55, 45 and 25 instead of jumping it from 20 degrees. Tried our luck, but again this was in our pilot scale. After 11 hours we gradually see more and more amorphous showing up. So, we did start with form 1, but over a period of time more of this semi amorphous form 5 that came up over time, and now we are kind of stuck. There's all this nice literature on CSTRs, and we're like, what do we do about this, what's really happening in this situation, right. And we try to analyze what are the differences between the batch and the continuous process for this polymorph control. So, in batch it's a reverse anti-solvent addition. So, we are adding it into water containing seeds, whereas here it's simultaneous. So, mode of addition is different. In the batch the anti-solvent is very high initially, which we know favors form 1, whereas here it's always the same ratio, right, anti-solvent to solvent is always the same ratio coming in. So, it's not like it's very high initially and then drops. And in the batch lot of seeds are present, yeah, comparatively, because all the seeds are there in one go, whereas in continuous the percentage is always 5%, it's very consistent. So, these were the differences, right, but we can't help any of these because this is the way a continuous process will operate, there's nothing we can change about these. The other thing was the back mixing in the CSTRs, right. So, we are adding these 2, there's always back mixing in CSTRs, and that's why we started wondering, would a plug flow reactor work better, right. But I'll talk about this a bit later, but there's a lot of publications, and we have burnt our hands in the past as well, where we used plug flow reactors, and they typically start choking over time because there is fouling that happens. So, plug flow was not the preferred option, but we did want to reduce back mixing, and that's where when we discussed with both Vijay Kriplani and Professor Anil and what he had in his lab, we looked at this reactor called an ACR, which is also in the IIT Bombay lab, right, which has 10 little cells. And this was basically, I think, designed for heterogeneous reactions. Yeah, so each of these cells has a little baffle inside, and one sec. You can see this thing just shakes. Yeah, so that's its mixing mechanism. So it just shakes, and you feed it in from the bottom, and it goes all the way through the 10 cells to the top. And we were honestly relieved and thrilled that when we ran this, we got form 1 consistently from this reactor. Right? So what really changed? Earlier we had 3 CSTRs or 4 CSTRs, and they were big, but these are 10 little CSTRs, almost eliminated back mixing, right? And you get very, very uniform mixing to begin with through this. So given this, the ACR worked out really well, and we said, okay, let's optimize the ACR. So we did some classic crystallization optimization. I don't want to get into detail, but basically, splitting the water addition, seed addition, temperature, playing around with all these parameters, and we finally said, no, we will work with, yeah, thank you so much. So we said, finally, we'll add all the water containing seeds in the first cell at 65 degrees, and we need at least about 15 minutes, at 65 degrees to get it, so, to get the maximum amount crystallized at 65 before cooling it down. And so we crystallized in the ACR at 65, followed by cooling to 55, 45, and 25. And we ran it in the lab continuously for 7 days, and we could see very crystalline form 1 even at the end of 7 days, right? So this was literally 24/7 operation, and this gave us a lot of confidence that this process is going to work. So I think this whole, and a key learning or takeaway for us here was this back mixing can be very, very important for controlling the polymorph, and by using this kind of setup, we were able to really tackle the problem. And we also looked at further with some crystallization kinetics, and this was more of developing a process understanding. This was done by one of our employees, Shivani, who did her PhD with Professor Zoltan Naj at Purdue, and so she developed a kinetic model for crystallization for the ACR, where we looked at effect of residence time and all of those. So developed a UV method for calibration of the concentration, tracked the concentration versus residence time for crystallization, and basically, fitted to these kinetics using a GPROM's flow sheet model. And with this, she was able to predict both the concentration. This is actually, when you say concentration, is the mass fraction, so it's how much crystallized out, right? Measured versus predicted at the as a function of residence time, and also the particle size, measured versus predicted. So it was fairly good and close. I think it's hard to get anything that's really more accurate than this. And this also gave us confidence in our process understanding and how we want to scale this up. So I touched briefly upon one of the fouling where we wanted to use PFRs. So while we had this established in the lab, the big question was, how are we going to scale this up? Because practically everybody that we talked to and heard at conferences said the biggest problem is going to be fouling, and many articles on this, even with CSTRs, over a period of time you see this incrustation. And this actually happens at the time of nucleation, or rather it happens later too, but it's worst at the time of nucleation, right? So we really, if we can avoid this at nucleation, then we can control it later on as well. And for this, I think CSTR is fundamentally a bad design, and we knew it's not going to work for us anyway. So the reactor we went for was this RTR, which is from the same AM Technologies who had given us the lab scale ACR, right? So we had this RTR from them, and this is like basically it looks like a plug flow reactor, but inside it's split into you have these discs, so it's basically split into 10 compartments. So you flow through essentially these compartments, right? And each compartment in some sense can be thought of like a CSTR, right? And as it's flowing through like a plug flow, there's really, again, you've eliminated almost the back mixing. So, so that was the advantage of this, and I want to show how it actually, would move. So it would have this, oops, sorry. Yeah. So it'll have this rotating motion, right, with an inside agitator shaft, And the advantage of this motion was that it could, you have a very good, it's almost like sweeping through the surface, right, very close to the surface. So that helps to minimize fouling, right. The fact that you have good shear near the walls of the reactor is the key to, reducing fouling. And with this we were able to optimize it, various temperatures, operating parameters to say that we want to, optimize our filtration rate. So this, we actually rented the machine, took trials in the pilot plant, and it worked really well, and we said this seems to look good. We then had to, if you remember, we had the ACR with 3 CSTRs, so we also wanted to have now the RTR followed by the CSTRs, for which we used computational fluid dynamics to custom design the agitator and geometry and all of that, all keeping in mind that you want good shear, you want good mixing, but you don't want fouling, right? You want to eliminate fouling, but you also don't want to mix it so hard that you break the crystals and lead to attrition. Because if there is attrition, again the filtration is going to be very slow. So with the combination of, CFD design for the reactors, we were then able to get a whole design that had the RTR plus the crystallizers. And what was very interesting to us was, this is how the crystals look, some images of the crystals from a batch crystallization. So remember, it's reverse anti-solvent addition, so high supersaturation, fine crystals. And then this is what the ACR in the lab looked like, and the RTR was even better. And just one point I want to mention here, so now in our commercial plant, we actually took batch crystallized slurry and ran it through our filtration setup, which I'll talk about in a bit. And we used to get around 50% wetness of the cake, so it's quite wet because the crystals are fine. When we took from the, RTR and ran it, we got about 35% wetness. So that shows that the crystal size has really improved, and we have much better filtration with the RTR. So I thought this was very impressive in terms of the particle size control that it afforded us. So this is what our setup is. RTR, actually we had 2 RTRs followed by cooling down to 25 degrees. And we then integrated with this rotary pressure filter from BHS Germany, which has a feed zone, so continuous, right? You feed it in here, right? As you feed it, it gets filtered. It then gets washed, in this case with water or IPA water, press dried here, and then there's a knife that cuts it, and this gets, the wet cake gets unloaded. So all this just happens in a continuous fashion, and so we basically had to size this so that the filtration rate would be able to handle the steady stream coming in from crystallization. In fact, from reaction all the way through crystallization. So this filtration setup has to be able to handle exactly the same volumetric flow rate that's coming in through here, and then discharge the wet cake. So this was run for several hours, and we found the whole system worked really well. However, we did have challenges when we were working this filtration system, because the crystals were fine. We had a lot of pass through initially. We optimized various parameters on the RPF. I don't want to get into detail, but I'll say a critical aspect was the filter cloth, the selection of filter cloth, to ensure that you don't have pass through, but also that you have sufficiently good filtration that you can match the upstream feed rates, flow rates. And then further to the filter, we also wanted to dry this compound in a continuous fashion. And this was a huge challenge, because we wanted a dryer that was GMP suitable and will also dry it fast enough. Imagine you have wet cake coming in, which is about 25 kgs per hour, right? And it has to dry 25 kgs per hour from a wetness of, let's say now 35 to 40%, down to the trihydrate, which is around 4.5%, right? So that has to happen fast enough to meet your whole thing. So everywhere, it's the timing has to be impeccable, right? And we felt the fastest dryer was in, which is not going to be huge, right? It also has to fit into a clean room because it's an API, would be a fluid bed dryer. And we conducted these fluid bed drying studies in a lab where we could see that from around this 40% water, you're able to drop to nearly 5%, which is the stoichiometric hydrate, within 15 minutes or so, right? And this is the temperature, inlet temperature in the FBD. So it's around 80 degrees in this case. And we further increased the temperature also to 90 degrees in the FBD and did the study, and again you could see within 15 minutes we are able to dry this, and this gave us confidence that FBD could be the right kind of dryer to help us dry this efficiently. And we came across this continuous FBD, which again has 4 compartments. So it has, I'll just show this picture and then this. So you basically have wet cake falling in here, and then it gets dried and passes from zone to zone and gets discharged through this. So it's a totally continuous fluid bed dryer, and this is what it looks like inside. So and these are weighers that are like between each compartment. So with it will go under this weir and then pass through, though some of the fines may just go over the top, right? And this is something that we got from GLAT, and it you know, we've recently taken a lot of trials, and you know, it's actually working beautifully. So you can see here with various parameters, right, with a residence time of from between 9 to 18 minutes is what we varied. We are actually able to get a water content, you know, less than 5%. So we started with 43% wet cake, basically essentially water, and we're able to dry it down to, you know, 4.5% with a residence time of just between 10 to 20 minutes. So that's how efficient the drying is in this continuous FBD, right? And there was one challenge here, which was basically when you look at the RPF, rotary pressure filter, it has these cells. So when it cuts the cake, it comes out looking like a, you know, like a chocolate bar essentially, right? And we can't just load a chocolate bar in this FBD because it will just, you know, sit at the bottom and it won't fluidize. So you have to commill a wet material, which again is something very tricky and what we did not think about initially. So there are all these little unexpected things, right? If you're loading it into a batch dryer, right, you just have an ANFD or an agitator which will just break up your wet cake, and you don't even apply your mind to the problem because it's routine. But here we had to figure out, how do you take these chocolate bar chunks that come out of this RPF and, you know, break it down to powder that's actually going to get fluidized in this FBD, right? And so we had a comill that was put in place with GLAT. Lot of challenges in sizing the comill, getting it right, you know, getting the kind of right wetness, because if it's too wet, we just form a pasty layer. And for those of you who are familiar with the comill, you can just coat the inside of a comill and that's it, you're done. There's nothing further that's going to pass through it. So getting the right wetness and making sure it's going to, you know, go through the comill at the right pace was also something that was very, very critical. So this byproduct filter and comill actually gave us help, while the rest of the process in retrospect seemed simple, but though it wasn't quite. Yeah, so this was our final integrated setup where we had these 2 RTRs followed by 3 CSTRs in sync with an overflow wear mechanism getting into a continuous filter and then into this continuous dryer, right? And there's actually a comill in between. So that's how it goes all the way through. So with that, you know, I just want to also mention that this has been run now, the end-to-end stream right from the first reaction all the way through drying has been running, you know, demonstrated running continuously, and you know, we are in the process of, you know, the final aspects of the PQ and further filing. So that's where we are on this. And I would like to, you know, thank Dr. Rajiv Rehani Buddev, who's been heading the API vertical at Dr. Reddy's, who's, you know, very, whose conviction and really championing this whole effort all the way through. It's been several years of effort, but we are seeing the fruit of it now. You know, other colleagues at Dr. Reddy's who did a lot of the crystallization trials in the pilot plant, Sudhakar and Srinivas, and of course the PI, you know, process intensification team, Vijay and Madhav, who've been holding our hand all the way through, and also AM Technology, Robert Ash and Gary and Christopher Gaunt for, you know, helping us design the AM, you know, all these reactors and suiting us for crystallization. And finally, GMM, Fodler and Tri-Diagonal, who helped us with this whole CSTR custom design that will eliminate this fouling. So thank you all. I don't know how I did on time, but yeah. Good. Wonderful. Yeah. All right.
Yeah. Few questions, if you have.
Thank you. Wonderful talk. It's actually a comment to what Dr. Srinivas asked in the previous session. I think one of the biggest difficulties, I think, in going from batch to flow for crystallization would be the seeds, which is what you also mentioned, because seeds can play 2 roles. One is as a nucleus, where you have much better control in batch than in flow, because you have a batch which is a fixed entity. The other is on the other side, the impurities, where an impurity which gets stuck somewhere in your flow reactor could continuously lead you to a wrong polymorph or a wrong product. So both ways there are challenges, but I think you have overcome them very nicely, so congratulations. But those are, in principle, I think those are the two issues to be, they are very different from a reaction where most of the things are in solution, compared to crystallization where, as was rightly pointed out, nucleation and small impurities can have very dramatic effects on what comes out after crystallization. Wonderful talk, thank you.
Thank you. No, you're right, and I think anywhere where we also want to say anything is heterogeneous, right? Whether it's a reaction or these kind of things, I think the whole solid, dealing with solids, whether in a slurry or otherwise, also becomes an additional challenge. So, yeah.
Nice, very nice presentation, Dr. Srivijaya. I think for a chemical engineer or a scientist, this kind of unexpected challenges will become nightmares, especially when you are almost at the close of the project, when you committed dates for the filing DMFs and all kinds of things. How much time it took for you to optimize these from the batch process to the flow process?
I think it would take, I think Jagan will remember better, but I would say about 6 months or so. I think the really, I would say the turning point was identification of this reactor. And I remember going to Akima in 2018, and I remember Robert Ash, showing this reactor for, reactions. And the minute I saw it, I said, wow, this is what we need for crystallization, because there was nothing else out there which was really convincing, even though we had looked at it. So I think that was really a turning point. And the second was the selection of dryers. So I'd say the batch to continuous translation in the lab was relatively easier once we identified the right technology. Yeah.
I think I had the same query as regarding the continuous seed aspect. I think that you have clarified. Does it mean that CSTS are good for amorphous? I don't think that's the case.
So after nearly, I'll say, I have to confess, after nearly 2 decades, where my primary focus has been in crystallization and solid form, as you're aware, initially, I still have to say I don't understand the subject, right? Because it's very, very complicated. Every API has a mind of its own, literally. So we don't know what it's going to do. So I think this is very much a case-on-case basis. But I mean, there are cases where I think you can get good crystalline polymorph control with CSTRs as well. And Eli Lilly has published those. Yeah.
This is something that I'm asking because I'm not aware of, right? So what you have showed is not just a crystallization, but more of a polymorphic homogeneity that you're able to make, consistency of a polymorph.
Yes.
And eventually fixing the crystal size.
Yes.
To enable a filtration. What kind of sensors do you think might actually help in the future to make sure that your process is actually running? Is there an online version of PXRE?
Yeah, no. So I think, well, there's a Raman. Raman can tell you the polymorph, right? We were confident enough now of the form that we didn't opt to put the Raman in there, because honestly, I think when we looked at implementing PAT in manufacturing, it is a little complicated, and I think Rajendra could tell us a lot more about it. But having the model that's valid and all of these, all the requirements that come with it, it's a lot of headache, to be frank, right? Whereas using it for process understanding in the lab is of course, we should do it all the time, and we do it. But to have a PAT in the plant, I think having those models maintained and all is, and he can comment more on it, but it is a bit, it can be done, it's not impossible, but it requires a lot of rigor. So that is one thing. But Raman can do it. The other thing, that's simpler models, right? They're simpler pattern that I would say, like UV. So UV will tell me the concentration as it's coming out, right? Or the concentration of the filtrate. We have a turbidity meter to just check if there's any pass through, right? We have conductivity meters all over the place, right? So these are very simple things. Like Raman is more, the spectra and all is more complicated, but conductivity, and this I learned from GSK, right? They use it as a signature. Right, it doesn't tell you one particular thing, but all across it's a signature of what's happening.
Once you're
Yeah, once you fixed your process and you just monitor. So we have now so much data coming out, so many sensors, that we can actually use all these very modern techniques, right, to analyze this data and interpret when a process is in a state of control and when it is not, and that's a whole different topic. But just to answer it simply, yes, I think there are enough sensors that we have put in place that will know if the process is in control.
Fantastic. Okay. For a non-specialist, a solution guy. When it comes to drying, a lot of time, there is intrinsic danger to drying, especially on large quantities, and maybe sometimes an explosion. There's been cases.
Yeah.
So this flow chemistry, is it getting the drying safer, or there are intrinsic danger to consider which we don't know yet?
Well, I think the two are independent. I think what you're saying is correct, that in drying, and in fact even for this, we did very extensive analysis on the powder safety. We even did this fear test where we sent 1 kg of material somewhere to look at the explosivity and all of these things before we could put it in the FBD. And we have interlocks where basically with the data GLAD guaranteed that it can withstand up to some 12 bar of pressure, if I'm not mistaken. So that to ensure that even if there is an explosion, we have data to show that it will not exceed 12 bars. So you are absolutely right that the process safety has to be very thoroughly studied, especially within FBD. But I don't think it necessarily links to the flow chemistry aspect of it unless you have hazardous reagents coming through. In our case, we didn't. There was nothing that was particularly hazardous in terms of explosivity, but you're right that if there is, then you will need a mechanism to wash it off before getting it to drying.
So I think just to extend your thought, FBD is going to be common, either it is flow or batch. But before FBD, I think there is a wetness of the material coming out. So it's going to be safe, to my understanding. Yeah. Any more question? Okay. Thank you so much, Srividya. Give her a round of applause for excellent talk.
Thank you.
Thank you, ma'am. So we'll be now presenting the honorable mementos. I request Dr. Rakeshwar to hand over the memento to Professor Nangia and Dr. Srividya. Okay, thank you, sir. So I'll now request Dr. Srinivas to introduce the last speaker of the day.
Thank you, Rakesh, for chairing in multiple sessions. And before I introduce Dr. Rajendra, we were also supposed to have Mr. Vijay Kriplani to deliver a lecture and also share his insights about how this flow chemistry has evolved in the country across various sectors, be it fine chemical to pharma. Unfortunately, due to certain last-minute flight changes, he was not able to make it. We'll hope to have him very soon in any other event in the coming future. With that, we will go to the last speaker for today's conclave, Dr. Rajendra Kumar. He is a good friend as well as been associated with Dr. Reddy's. Dr. Rajendra Kumar has more than 30 years experience in pharmaceutical industry. He is currently working as a senior director, synthetic laboratory at United States Pharmacopoeia. Dr. Rajendra started his career as a process development scientist on new chemical entities at Dr. Reddy's Research Foundation, which was earlier there in the Miapur campus. After working for 13 years, he moved over to companies like Sigma Aldrich, and then he was associated with AstraZeneca, subsequently PI Industries in Rajasthan. Before joining USP, he was a vice president heading the chemistry developmental R&D of chemistry at PI Industries. Dr. Rajendra, in fact, is probably a good classic textbook example of what one needs to be in pharma industry. He's not only a good process development, very good scientist himself, but he has a very extensive knowledge of quality guidelines, regulatory guidelines, project management. So he's all integrated into one. And he has conducted multiple workshops and courses for project management, regulatory guidelines. I have learned CAPA, what is also popularly called as CAPA, from him about how one has to go about it. So with that, I will request Dr. Rajendra to give his lecture. It so happens that it was not planned, but the last thing in any pharmaceutical development or any fine chemical is called quality. And he obviously comes from USP, so I think we are kind of moving the day on in the right direction.
Thank you. Thanks, Srinivas, for your generous introduction. And just I want to tell you a few background of about me coming over here and presenting. Before that, Srinivas sent me the agenda and the speakers just 2 days back. I saw that 2 days back. Probably had he sent along with the request, you would have left after Srividya's lecture, right? Not, and now that Professor, all the big professors here, excellent people who are well versed with the flow chemistry for last few decades, and they spoke. And now me being the last person, and probably I'm the youngest person doing the flow chemistry, practicing flow chemistry. You can hear what kind of a nice stories that you can listen from a naive scientist who are first time entering into the flow chemistry, and you can build up the courage. Those who want to start flow chemistry, definitely I am sure my presentation will give some kind of a booster for them. I will start. And I'm going to talk about USP India's flow chemistry journey here, how we started. And in the process, I will talk about a little bit of the microgrant project, what these microgrants are about. This is a very unique to USP. Of course, most of the industries do have this kind of practices, but maybe names are different. And how the flow chemistry started with us, few examples. Along with that, I'm going to talk. What is the microgrant project? This is the projects where USP encourages young scientists to come out with a proposal. Once you submit your proposal, if the microgrant project is accepted, you are relieved from your regular lab work for 3 to 4 months. You are not pressurized for deliveries, how many molecules is synthesized, what targets, no project management reviews, and so on and so forth. You are free to do whatever that you can, what you want to do. They will give small amount of the money also, $5,000 to $10,000 they give. You just work for 3 to 4 months, submit your report, then again move on, go back to your regular work and keep working. This is to just encourage the scientists to do about it. This is one part of the story, how the microgrant starts. As far as I am concerned about the flow chemistry, I want to tell you one thing, that almost from 2000 onwards, the present chairman of Dr. Reddy's, Dr. G. Prasad, used to say, this is a synthetic chemist never changed in the last century, whereas other sciences have moved so far, so fast. Look at what started in 1990s about the chromatographic techniques, HPLCs, GCs, now where they are. If you see that last 30 to 40 years, but for little bit of automation here and there, your batch processes remain more or less constant. Today also you can do the same reactions which were installed almost 30 years, 40 years back, the reactors. Nothing much has happened. I don't know why. And this is one of the most intensively worked area being the pharmaceutical industries, but nothing much has changed. He always used to comment. I first heard in somewhere in 1997 or so, very recently, as recently as 2 years back also he said the same thing. It is high time that process chemistry changes to a new arena, new ways of doing things. Also I should say, because we didn't change, not many youngsters want to come to the synthetic chemistry today, especially in industry. I'm not very sure about the academics part of it, but definitely people, if you ask youngsters in our generation, synthetic chemistry means that is something very exciting. But today people want to go to analytical chemistry, quality assurance, so on and so forth. Not much encouragement to synthetic chemistry because we didn't change.
However, coming back, that's one part of it. Second thing, in 2018, I attended one course in Bombay on the flow chemistry. Professor Anil gave his presentation, and many other eminent speakers also spoke in that. It was really exciting, where the world is going and where we are going, where we are up to. Then I went to, there was a stalls were installed. We went all into the stalls and started asking how much is this instrument, how much is that instrument. Everybody said $35,000, $40,000, $50,000 and all. Again we took the back seat, this is not our cup of tea. We went back to the labs again. But however, then one more step happened pre-COVID. We happened to visit to ICT. At that time one of our colleague, he asked how about going to the flow chemistry lab and see how the labs looks like. After going there and monitoring those reactors very closely, I didn't find that it's such a complicated thing to start with. When you want to really fully equipped reactor, if you want to say, it looks very complicated. But when you look at the basics, what is required to start a reaction, I find it not that difficult. That was the time when we said we'll write a microgrant and see how it works. That's how we started the flow chemistry. And we have customized existing photochemical reactor to a flow reactor and explored olefin and RGMs, isomerization reactions. These were one of the toughest reactions that we are facing in the lab. I will show you why they were tough. However, after completing the microgrant, established a proof of principle for a few of the reactions which were otherwise finding it very difficult to do in the batch process. Observed improvement in percentage of the product formation, reaction profile and time. Reaction profile is very important for us. For any purification, if the reaction profile is good, it becomes much easier for you to do the purification part of it. Generally in USP, we make around 100 grams, 200 grams materials. We don't make tonnage scale, but even to make that 100 grams, we used to have tough time. Let's talk about few of the things, flow chemistry in the USP. When we submitted, successfully we completed the microgrant, we submitted the report, and it was given due importance because that was the time when pharmaceutical continuous manufacturing initiative was going global. FDA started talking about it, Europe started talking about it, and everybody started talking about it, that it's a continuous manufacturing is required to improve the quality of the systems. Thanks to COVID. COVID has further enhanced this concept for two reasons. One is supply chain resiliency. Lot of drug shortages were there during the COVID time. Quality issues have cropped up. Second thing is that sustainability. These two, supply chain resiliency, as Professor Nangia was mentioning, today's the biggest buzzwords are sustainability and supply chain resilience and quality. One part answer for these three questions probably finds in flow chemistry. That's the reason why people are started seriously looking into that. And having said so, once we completed with $5,000 we were given, and we put up a reactor here. You can see this. This is our Wright Brothers aircraft kind of a thing, where whatever that is available, we assemble it. This was supposed to be our regular photochemical flow reactor, photochemical reactor per se, and out of $5,000 what you will get when you go to the market. Then go to the Secunderabad, then you will get everything there, whatever that you want, electronics, mechanical, whatever, civil, everything you will get there. They bought a few bulbs, few tubings, and we went to HPLC guys. We asked them, do you have any condemned, spoiled, which are not working HPLC systems? They said, oh, there are plenty, go and take it in the garage, there are many. We opened few, we took out those pumps, started using this. After completing the project, we returned $2,000. Out of these $5,000 what we got, we returned $2,000 because that's only the amount what we have spent. But look at the reactions what we have done. Okay. The next part is that capability of the, once we submitted that, as I said before, we assembled an aircraft which was as good as Wright Brothers aircraft almost 100 years back, or 150 years back. Then we proposed for a F-16 aircraft. Then we said, now that we have given the proof of concept, please give us big money so that we can go ahead. Can you believe it? We got around 200,000 grant as a grant first time. We got such a big grant that, okay, now that you people have successfully demonstrated it, start working. And because that was the time when very high focus was given for this continuous manufacturing. And we were at the right time at right place, we got that money, and this is the reactor what we bought. I think Anil also, Professor Anil also gave advice that Rajendra, don't think too much, go ahead and buy this reactor, it works like horse, working hard, please go ahead with that. Okay. Now, we bought the state of art equipment, collaboration with academic research institutes, that really helped. Initial baby steps were really helped us when IICT colleagues have helped us in identifying the reactions, training 2 of our scientists there, and they also helped us in identifying the configuration of the reaction pairs and all negotiations. And finally, we are in the process of doing reactions now. Probably we may start working on few of the APIs, especially for the African and some of the Latin American countries, and those projects we are about to initiate. From very small setups, very what I should say, very baby steps to slowly we are graduating to the next stages. Few of the reactions what we have successfully demonstrated here I would like to mention. Oxidative decarboxylation and a few of the EZ epimerizations, and also one silicoxib API which is very common, which is very easy to do, because initially we want to have some experience in the reactors. We did few of the known reactions. Coming to the ketorolac RCB and RCC, these are the 2 impurities, catalog impurities, high demand in nature, very okay. It is a simple decarboxylation followed by the oxidation that we need to do, ketorolac RCC, and if you do a hydrogenation there or reduction, you will get a ketorolac RCB. This is the batch process where we used to do. Reaction was so low, yields were only 12%. Still that could have been okay. Long reaction times, polymerization was observed, though HPLC shows that, but mostly your flask ends up with a black material, tarry material. Could not derive ketorolac RCC on a large scale due to the inconsistent and poor yields. Despite we trying so much, we could not do the reaction properly. Project was dropped due to, because we were not able to produce the right reaction. We would have done it, but in the given time, given the conditions, because they could outsource it somewhere else, finally we dropped the project. But when we got the flow reactor, again we attempted this particular reaction with using oxygen pump, the BPR in between. Successfully we could produce the, if you see that ketorolac RCC is 38%, RCB is 13%, and decarboxylated impurity where this completely knocked out at 30%. And this earlier I showed you, it was 12% only, but the reaction was very messy. You can see the chromatogram here, product is so clean, these 2 are the what we wanted, this is the decarboxylated product, and we could quickly purify. Purification we did with batch process only, but as far as the product formation is concerned, we could successfully develop this particular reaction using the photochemical reactor. Coming to the next step, this is another step, as Professor Nangia was talking about thermodynamically controlled and kinetically controlled reactions. Getting this E isomer, Z isomer is very difficult. Unless you go for total synthesis, it is very, very difficult for us to get this kind of an isomer, and hence we went for the again photo flow reactor only. We tried our luck for this kind of an isomerizations, because earlier we had some experience of EZ isomerization using the photochemical reactions. Whatever the photochemical reactions experience that we had, the same thing we replicated in the flow reactors also. Here if you see the batch process, wherein the product formation again was only 12%. When we went for the flow reactors, we went up to 34%, and starting material was product was around 33%, and starting materials were around 54, 38, 66% or so. There is a significant improvement when we have done the same reactions from batch to this, and not only the product formation was good, but also the reactions were very clean, wherein we could do a simple recrystallizations rather than going for a prep HPLCs or very high intensive techniques. Reaction time is decreased significantly from 23 hours for the batch process, whereas when
whatever that we assembled, it took 6 hours, whereas in the regular reactor, whatever the commercial reactor took just 1 hour. The product formation was very high, 34%, and unreacted starting material was 58%, and other impurities were only 0.44%. When the other impurities are less, it becomes very easy for us to do the purification part of it. 34% is a decent when compared with the 12%, and reaction should not be messy. The another and this is another impurity what we could synthesize using Zelendak RCA, whereas again this is again a Z isomer, here we want an E isomer. We use the flow chemistry here. It is a 3-step process when we are doing in a batch process. We have to use a metal palladium chloride as a catalyst, prepare to HPLC for the purification. We did not have any choice because the peaks were so close, and it is very difficult for us to isolate or separate from the simple gravity columns or a flash columns. Only preparative HPLCs were taking care. Project lead time was 4 months if you want to do it a 15 grams material. That was the time, because in prep HPLCs your injection capacities are so low and the resolutions are very less, and it becomes all the more difficult for you to get the purified material. And here also we have developed a continuous flow process, again a single step process. No metals were used, straight away we went for the direct flow reactor using using this 230 to 580 nanometers filters, and purification this time was done by only simple recrystallization. Because the product formation was good and the product was very clean, I can show you the clean, still simple recrystallizations have helped us to improve the product, and that we could get the whatever that is required materials. Drastic reduction in lead time and the cost. From 4 months of time where the purification took almost 3.5 months for using the prep HPLCs, to almost it has come down to few days for us to purify the same materials, and scalability has become very easy. But however, this gave some surprises, because our experience was not so high, we could not identify what went wrong with this. But when we started working with the mercury lamp, after doing few reactions in gram scale, there is a color deposited on the PFA tubing. Why this color has come, we try to analyze, we try to give a lot of washings, but nothing has helped. The product formation was reduced to 10% from almost 40%, and root cause we could not identify why it has troubled like this. But we went back to the manufacturer, we asked them, they were also helpless. They asked us to send the tubing there, and we sent the tubing there, but we haven't heard from them what made this color to come. In a batch size of 360 milligrams, residence time we kept it as a 33 minutes, and solvent again acetone DMF. Solvent volume for every 1 gram we taken 50 volumes of solvent, and starting material was 71%, and product Zelendak RCA formulation was 32%. And as we are progressing, as the color developed, the product formation has come down. This was the trouble what we have faced. But again, when we asked for the tubing to be ordered and bought back, they said again it takes around 2 to 2.5 months time. We went back to the local markets, we bought the tubing, we performed the reactions, and what would have costed some thousands of rupees, we bought it down to a few hundreds of rupees, because that tubing was available here. And here we went back to the literature and looked at the Rosobengal is one of the materials where it is used as a sensitizer, and here it has helped to increase the product formation. Reactant volumes again 10 ml to 6 ml. Residence time we kept it as 33 minutes, and temperature we kept it 20%, 20 degrees centigrade. Product formation went from 44 to 50%. That is one part of it, and if you see that the reactions are very clean, either you have the desired product and you have starting material. No other product was formed which is more than 1%. Because of this formation, the reaction clean, and we got a good material, simple recrystallizations has helped to get the right materials here. This is 6 ml photoflow reactor what we bought it from the local markets, which we could successfully deliver the product. If you see the optimization part of it, we took 6 grams Rosa Bengal,
And these are the different residence times that we try to optimize. S20 DMF solvent we did not change 300 ml. Again at the different residence timings we got this product range from 45% to 50% to 44%. This is the range what we have got. This is the product profile. And this is Cylinder API and desired product is E isomer is 44%. This is pretty good percentage of the product that we have seen for the first time, this kind of reactions. Another one is the silicoxib. This is again an API. Just this we practice. I am sure every flow chemistry scientist will perform this reaction, which is a single step reaction, very easy to perform. And we try to put up we got the good result again. The product itself got 94%. After the purification, straight away they got the 99% of it. It is a single step reaction, and we have done it. Now going forward, we have around 1300 products under our portfolio where we have the technologies with us as far as USP India is concerned. Our catalog is around 3800 or 4000 products which are there in the catalog. We own the technologies for 300. Our target is going forward at least 15 to 20% of the reactions or the product should be tried, at least 10% should be successful every year what we are going to manufacture. And days to come, we want people to try, each scientist will have 2 fumets, one fumet will have a continuous flow reactor and other fumet he will be trying. If that does not come, then they have to go for the batch processes. This is the ease of operations, and the advantages of flow chemistry is completely different. You can control so many things, as Professor Nangia was mentioning. You can control the pressures, you can control the temperature very accurately, you can control the timings of the reactions, and especially process safety. You do not have the problems of the process safety to think about, which otherwise a batch process to do 1 gram scale you will be really scared of doing it, but in the flow chemistry that process safety is taken care. Also the containment issues, when you have everything is completely controlled and everything under flow, and it becomes much easy for having the process safety controls also. Hence, I think going forward as synthetic chemists we should explore more and more on the flow chemistry side, and this is one classical example. We do not need big money to start with. Yes, when you want to do a very complex reactions, but Dr. Srividya was mentioning those kind of things definitely we need, but to start with simple reactions, simple setups also will help. Thanks Dr. Srinivas once again for giving this opportunity to present whatever that we did in the last 1 year or 6 months or so. And this is the team. Ms. Nagaraju is sitting here, and Bhushan Prasad Srinivas. Mohammad Taqi is the guy who really did lot of work in designing these things, going around writing the reports and all. Of course, myself and Brunal were taking care of these projects. Thank you.
Thank you, Dr. Rajendra. I think it has covered a very important aspect of the product, because quality is defined by clearly identifying the impurities, and some of these are not otherwise easily accessible.
Yeah.
And looks in all the cases I noticed that you didn't really go back to the synthesis. You have used an API and then.
Correct.
Am I right?
Correct.
I think in all the examples.
Correct.
Exactly. So with that, we'll have a few questions.
Are you up for selling these impurities to anybody?
No, we give it to our parent organization. They do a lot of, before that becomes a reference standard, they do a lot of testings further. Then they go to the production and reference standards. They use it as a bulk raw material, whatever that we give. After that they do the collaborative testing in 3 different labs, and then they certify it as a reference standard. That's a 1 year process afterwards.
Okay. Yeah, when you, very nice examples, when you get a cis trans or an easy isomer by photochemical route, and you are getting some ratio of, so do you need to separate them, or can you just run through the cycle again till it goes to the desired isomer?
Yes, we did that multiple times.
Yeah, multiple times, yeah.
Sometimes it helps to go to certain levels, but after that reaction,
it reached an equilibrium.
Then it comes to a stage that where beyond that it will not go forward. That's the stage where there it helps you at how much residence time that you want to keep it. There, that's the reason they try different residence times, and they try that. Yeah, recoveries of course
Yeah,
we can.
that's the thing. Sometimes separation is not so trivial.
I think my question was essentially given by Ashwini, because essentially most of your systems are like a photo switch. And so maybe for the younger people, there is a very simple equation. This is the absorption coefficient plus the quantum yield of the transformation, which is equals, in the Z form, equals the absorption coefficient from the E form multiplied by the quantum yield of the back transformation. And that one you cannot beat normally. So at some stage, you will always get this equilibrium. And so my question is, can flow beat physics? Okay, so that's one of photophysics. But this is a bit, of course, I'm joking, okay. But could you put maybe back some of the slides like Sunindak?
Yeah.
Because this is me as a helicene chemist. Is there a possibility, especially in the Z form, to get a 6-pi electrocyclization? Because photochemically, your system is ideally suited to form the CC bond in between, and that could be your byproduct, especially if there is some kind of oxygen and everything, and then you're doomed.
Yeah, when we were doing these reactions initially, we haven't understood still honestly why this coloration has happened, what kind of a reaction that's undergoing. And also we have one of our scientists is a computational scientist. He does a lot of modeling, theoretical modeling, and we looked at his support also, we took it. But so far we didn't have the answer that why this particular behavior of this
because
coloration.
the mercury lamp is exactly the kind of lamp we use in this is the Martin helicene synthesis, okay, and this is exactly here. You need just a catalytic amount of iodine usually, in order to speed up the the reoxidation to the aromatic groups, but this is a big danger. And then actually the next project where you have the CH3 groups, it looks like vitamin D, because you can have the photochemical 1,7. Okay.
Oh, yeah. Cyclization.
Basically transfer. This gives you also byproduct. This is so. I think I'm going to use some of your chemistry as exam questions.
Sure.
Okay, it's going to be great. And then finally, sorry, it's a bit. I'm not a photochemist, but I noticed that the first two topics that you took compounds which have intramolecular triplet, actually. Essentially excitizer, because you have these aromatic ketones all over the place.
Yeah.
So I was looking at this process that your compounds should self-immolate with oxygen, actually, because when you are doing the irradiation, basically you should get the energy transfer to the triplet state and then recombination. This was your design?
We actually, in a batch process, we simply did with using palladium chloride, and where we did the decarboxylation followed by the simple oxidations. Either you get OH or C double bond both. That interconversion is very easy for us. We try to make this compound, but most of the time we used to get very tarry material irrespective of what we did. Then we tried in the photochemical reactions, then it really helped. When we did with oxygen kind of a thing, really it helped us to get there under the photochemical conditions. No.
I think it gets through the oxygen.
Yeah.
No, certainly it has opened up. Maybe I can probably be corrected, but what I realize is, except for the vitamin D3 process, what you have mentioned, which is a textbook example of photochemistry at a manufacturing scale, but more than 100 and odd years of excellent photochemical transformations, we are not able to translate at a volume driven, purely because of multiple things. You cannot have that intensity. There is a lot of light plus heat impact and multiple things. I think there are a lot of clues what we have also gained from your talk, and some real examples. I mean,
if you see that these are all the axioms of the beta-lactams, and we were very uncomfortable in handling in the labs because the obvious reasons. But when we have started using the flow chemistry, it has become so easy for us to handle it, because if you want to synthesize this in the lab, starting from the raw materials, it takes very long time, and end of the day you may not get the required quantities, because this is the most thermodynamically stable, and this will be the most favored. You will be getting 2%, 3% in the reaction mixture. Again, isolation is becoming a big challenge for us. Hence, once we realize that this photochemical reactions really helpful in getting 20%, 30%, we are very comfortable in doing these reactions. Okay, and another thing, having said that, we make only 100 grams, 200 grams materials. We don't try to get the best processes to get, like, where you want to have 95% purity and 90% yields kind of a thing. Fit for purpose is our aim, and if you get decent amount and once we can do the separations, we are happy with it. But these reactions really opened up a lot of confidence and lot of enthusiasm in the scientists, so that most of the critical reactions which we are finding it difficult to do in the batch processes, now people want to attempt in the flow chemistry. That's a good sign what we have seen in the last 1 year or so. And there is a lot of enthusiasm is coming up. That's what the scientist needs. Once you see the initial success, then rest automatically flows in. Like, we are fortunate to have this initial success.
I have been always telling everybody that just take your HPLC tubes and 2 syringe pump, 2,000 rupees, you can start doing flow. So I'm surprised why people are still.
And that's why, that's what I'm telling. And I think these big reactors, and once you say that,
those are only once you get good results and you are looking at commercial. But
yeah,
just pick up syringe pump, which are there everywhere.
Exactly.
Syringe are 3 rupees.
Exactly.
And tubes, HPLC tubes are lying in every lab anyway.
That's what I want to tell all the younger generation scientists, that money should not be a constraint. If you are really using the science, money should not be a constraint.
It's less than their mobile bill sizing.
Absolutely,
sometimes I feel.
Absolutely. I do agree.
I think so. There was a good message for all the younger scientists. Hopefully, we'll have more. I do find it as a challenge. Right now, I think the flow chemistry team members are a minority. For every 10, we have 0.1. Maybe we need to have more. So with that, again, I think thank you, Dr. Ajinder, for covering a very important aspect and opening up, multiple thought processes. With that, let us give a big round of applause.
Once again, hello everyone. So we are now reaching the concluding part of this particular conclave. So it gives me immense pleasure to give the vote of thanks here on the behalf of the entire drills community. I extend my warmest gratitude to each of our distinguished speakers today who have taken out their time from their busy schedules to have come and given a talk here. Learning has been a never-ending journey, as we all know, and thanks to all of your lectures, this has become even more joyous today. We have been able to cover a lot of wide spectrum, starting from the basic theory behind flow up to downstream processing. Thanks to all of you, really for all of that. Further, I wish to also extend my sincere thanks to all the distinguished invitees, delegates, guests, staffs, and students present here. I wish to thank all the organizing committee members, the significant contributors from the IT department, HR department, the finance and the purchase departments as well, and to all the staffs and students who are assembled here. I'm sure this conclave has been an extremely enriching experience to all of us. So looking forward to more flow chemical conferences in the future, and also looking forward to a lot more presentations in future conclaves where more kids would be probably coming here and giving talks. So looking forward to all those kinds of beautiful moments in future. Thanks once again. Let's all meet outside for high tea and networking.
We can announce without laptop. I think Rakesh is the content.
I just took opportunity to advertise this conference, which is going to happen in the month of July, 4 to 7. And this is going to be a Silver Jubilee event by CRSI in collaboration with Dr. Reddy's. So we are expecting around 600 footfall. Yeah, in Dr. Reddy's.
So it doesn't say anything there.
So it's gonna be,
Date also is not there.
so it is there in upcoming slides. So it's gonna be on, as I said, July 4 to 7. And I think I have to run through the presentation quickly. So I think everybody knows how to reach Dr. Reddy's. And then this is the facility that we have where the conference is going to held. And we have got accommodation negotiations with various hotels. And we are expecting close to 400 to 600 footfalls. And we have a capacity of 600. And this is the convener, this is the co-convener. Thank you so much. So please register and try attending this conference.
I'm sorry. Thanks, Rakesh. I think as Dr. Rakesh mentioned, this is the 25th year of CRSI, which was Professor CNR Rao was the founder president of this. So what I understood from our current president, Professor Uday Maitra, is they will do a small event on 3rd at Bangalore, where Professor CNR Rao is there. Then everybody would come on 4th to Hyderabad, and we'll be having this three-day event. Half day on 4th, and then 5th and 6th, 7th will be a half day. So I believe also, thanks to him, I think first time CRSI might be doing it in an industry setting, which is probably also first of sorts. So we look forward to a great event in Hyderabad in July. I would say nothing to beat the crystallography symposium, which has set a Guinness record in the Novotel, but we'll still try to compete or reach some standard. Yes, definitely. Yes. Thank you. So, you have a tea for us? Okay, we should announce.
So we'll all meet outside for tea and networking from 4:15 onwards. Yeah, now.
Sorry.